lot for joining while traveling also. Good, very good. Okay. Yeah, Rajiv, you can, I think you can go ahead.
Yes, sir. Yes, sir. We are live now. Sir, we are live now. Okay, so let me start. So, very good morning to all of you. Honorable Director, sir, Head of the Department, dignitaries, my fellow colleagues, friends, and my dear students. IIT Tirupati is a young institute and crafting its footstep in every possible direction of flourishment in a rapid pace. Today, we are going to make another landmark steps towards the development of Department of Chemistry and as a whole IIT Tirupati. We are going to launch the 2 years master's program with 14 young, energetic, and enthusiastic students. It is a historic moment for IIT Tirupati and for all of us. We are fortunate to have 12 world-renowned professors with us to grace this momentous occasion and bless our department. The institute is progressing at a fast dynamics under the able leadership of our director, Professor K. N. Satyanarayana. We are thankful and privileged to have such a friendly, energetic, and enthusiastic person as our founder director. In spite of all the difficulties in this unprecedented time, his continuous support and encouragement is keeping us to move forward. We are also fortunate to have one of the young and energetic mind with more than 3 decades of experiences at first generation IIT Bombay as our HOD, head of the department, Professor C.P. Rao. The department is growing at a much faster pace since he has joined the institute. Now I request our HOD, Professor C.P. Rao, to give the opening remarks.
Okay. Uh, Good morning, Rajiv. Uh, Let me welcome all to this particular program. I'll just share my screen. Just let me know whether the screen is shared.
Yes, it is
Rajiv?
coming, sir.
Yes.
Yeah, yeah. So, hearty welcome to everyone, particularly on this occasion, the occasion being launching Masters in Chemistry at IIT Tirupati, which we try to associate with another academic component aspect, that is a bird's eye view at the excitements and the challenges in chemistry, in order to basically enthuse and energize our youngsters who are coming in into the campus for pursuing their MSc degree. So I would like to welcome all the dignitaries by showing one by one their slides. I welcome Professor P.
Sir, I
Balaram.
request you to make it on full screen mode. Then
Full
that
screen.
will,
Sorry.
yeah.
Is that? Yeah, I welcome Professor Balaram. I welcome Professor Satyamurthy. I welcome Professor Ganesh. I welcome Professor Saropal. I welcome Professor V. Chandrasekhar. I welcome Professor Umapati. I welcome Professor Jayan Murthy. I welcome Professor T. Pradeep. I welcome Professor G.K. Lahiri. And I welcome Professor Vijay Mohanan Pillai and Professor Sandeep Verma. Welcome Professor G. Mugesh. We also welcome our dynamic leader of the IIT Tirupati to get to this particular shape, Professor Satyanarayana, to the meeting. It is my pleasant duty to forward my hearty welcome to all students, staff, faculty, colleagues from the department and from the institute as a whole, and particularly the new students of masters and the PhD program. And there are several other guests who are tuned to this program. I welcome all of them to this. So the Department of Chemistry coexists with the institute, which was initiated in 2015 uh, by the same director at that time as a in charge director, Professor Satyanarayana, in 2015. And we chemistry department shares its teaching responsibility of the undergraduate by having 2 theory courses and 1 laboratory course to these undergraduate students. And this has been possible with the mentorship IIT Madras, and several faculty from the chemistry department have helped the chemistry program, and many other faculty have helped many other programs at IIT Tirupati, and of which 2015-16 Professor Rangarao, Professor Subramaniam, and Professor KKB and MNS Rao, and later on Professor again Rangarao, Mangal Sundar and Professor KKB. All these have continuously supported the teaching program. Not only the teaching program, we have an associated laboratory component which they have been responsible in building the lab as well. As you can see, our UG lab was built way back in January 2016. The session started August 2015. So within one semester of that, a very nice, very state-of-the-art undergraduate lab, as you can see with these and all with all the facilities of that. And at the beginning of that, our institute had appointed certain technical staff, Dr. Jagdish, Dr. Sanyasi Naidu, and a helping person, Dr. Hemant Kumar. All of these came quite early days of the institute and the department. And very recently, after I have joined, we have taken another technical person, Ajmer Nagu, and now we have a joint staff, Ajmer Jirwani, to help us with the office thing. Way back in 2017, the institute has recruited faculty members. So I wrote it as a starting faculty members. We have three: Dr. Arun Manna, Dr. Debashish Mandal, and Dr. Rajiv Bishwas. And during this period till the September 2019, Dr. Koteshwar Rao, who is the head of the physics, has taken the responsibility of the administration of the chemistry department. And lately, after the 2017, we have recently been added myself last year and Dr. Gandipan, and early this year, Dr. Gauri Prasanna Roy. So with this, we have a faculty strength of 6 at IIT Tirupati Chemistry Department. It's not that they are just sitting only with the BTech program. They have been very active and in writing the projects. In spite all the three, forgot to mention, all these three are computational and theoretical faculty. And in spite of that, they have been involved in writing the projects, proposals, and getting the project funding, etc. And at present, if you take a cumulative, we have 6 research projects to a tune of about 2.5 crore to about 3 years from now. And 4 of the research projects have been just submitted, not just submitted quite a while ago, which is a worth of 1.1 crore under review. These 3 faculty members have written these projects in spite IIT Tirupati itself helps the new faculty startup grant, which they got 60 lakhs. So that really shows that how dynamic these, and so the projects come from DST Inspire, SERB, ECRA, and of course mine is JC Bose and other SERB projects in this. So when 2018 beginning, the IIT Tirupati realized that we need to have PhD students, masters, MS come PhD. In this context, the Department of Chemistry has taken 3 students in the July 2018, which is 1 semester after the PhD program has been launched at IIT Tirupati. And you can see that Devendra Reddy, Raka Ahmed, and Yunus. Syed Yunus. And later on in 2019, one more student, Albin Joy. And 2020, we have another student, Rudra Shankarapati. And we have twice a year the program like any other place. The admissions take place twice. And recently in July, in spite of the COVID, we had conducted the interviews as usual online, and we have selected, and 5 of the students joined, and whose names are shown here, and they're all there now in the project. I also happen to take one of my former PhD student as a PDF to help in the ongoing work, is Dr. Rahul Nog in that. Of course, right now he's not here, but he's on role of that. And all these, my colleagues have been quite busily involved in working on research aspects, particularly in publications. And we can see that till today, we have total, there are 22 research publications are there, and starting from 1 publication in 2016, 3 in 2017, 6 in 2018, 4 in 2019, and about 8 already in 2020, and we predict that the number may go up to 12. And with that, we will be probably 25, 26 publications in about 5 years of span at IIT Tirupati. I must tell you that several of these are multi-institute and multi-authored publications where IIT Tirupati has a role in it, and a few of them are completely from IIT Tirupati. On the right side, you can see that these are all from quite well respected journals like the RSC journals, ACS journals, and other JFISCAM, JChemFIS, ChemFIS, FISCAM, all these we have publications in all that, and also in the materials kind of a journals. So inorganic journals, materials journals, and physical chemistry journals, and organic chemistry journals we have in that. We hope to grow on this direction. And Dr. Gauri Prasanna Roy has received a CRSI bronze medal in this year, 2000 February 2020. Prior to coming here, he was there at the SNU University in Noida, and then shifted in early January to IIT Tirupati. So Dr. Mondal, one of our colleagues, has taken up a review editor on the editorial board of biophysics journal. And one of our students, Raka Ahmad, got a oral presentation award when she has given an oral presentation at IISc Bangalore. Okay, with this, we could see that we have on one hand a BTech program of chemistry, and on the other hand, we have a, PhD in chemistry. It very clearly shows the gap between these two, and that is where we thought that we should bridge this gap by using a master's program. And that is what has been started in terms of taking shape, and which comes to today as the final shape of taking. So in this venture, we have planned to take 15 students, but we got 14, and the 14 names are reflecting over here. So as the MSc students are coming up, we have approached our director, and readily has assigned quite a good amount of space in the same temporary campus where we are presently, and by displacing certain other labs which were there and to the main campus. And so to our luck, we got a huge lab space, and we plan to equip this by July, but due to the present problem, it got delayed. But nevertheless, we will be through before November, December, when our laboratory starts for masters. So this is all going to be for masters lab. And we also have an instrumentation room. Right now, we haven't kept the instruments here, but we are just in the process of moving here. So, of course, we have started our MSc program with a standard classroom curriculum like anybody else, which is semester 1, 5 theory, 1 lab, semester 2, 5 theory, 1 lab, semester 3, 4 theory, 1 lab, plus a mini project, and semester 4, 3 theory plus a project of this. So all this goes to a total of 17 theory courses, 3 labs, a small project, and a major project, which is very much in par with everyone in the country and abroad. But that does not really make us to feel happy, because how are these MSc students can be knowing the world at all, knowing the chemistry? Chemistry, as we know, plays important role in every facet of life, whether it is a human life, in food, in environment, in agriculture, everywhere. So we thought we should have something that it could be informal. That informal thing which we refer it is here as the chemistry beyond classroom. We would like to bring the students onto the platform without this uncredited course, but this is being guarded by a faculty or a set of faculty members, and we will be mentoring to take up the students to take up a lot of projects, and try to understand those daily problems in the world and connect them to the real world. Beyond that, we also would like to connect all of us, not only our MSc students, not only our PhD, all of us, to great minds. As an initial startup, we plan to invite one renowned faculty members to interact with us once a month, and then probably we will increase the frequency to twice a month in the next semester, probably every week in a couple of years or so. And so with that, we will be covering more or less almost all the really connected people with chemistry, and we are hoping to look at that. We are also trying to push our chemistry gear, our chemistry PhD program by introducing weekly literature seminars, weekly research seminars, interaction with the eminent people, all this. And also, we wanted them to start conducting some seminars and symposia by that. Okay, obviously, all of this required a lot of infrastructural development. We have already procured a lot of routine lab equipment. I will not go through all of this. Hello, sorry. I got a call from Professor Balram. Okay, so infrastructure development we have. I think he's disconnected. Somebody please look into, I think Professor Balram is disconnected. Yeah, and lately we have acquired some high-end equipment, UV visible. Yeah, this call is from Professor Balram. Hello. Okay, he'll be joining back. So we have UVs, NIR, FTIR, fluorescence spectrometer, ICP mass spectrometer, which is with another department in IIT Tirupati we have. And we plan to procure, we are in the process of procuring a number of sophisticated instruments, plate reader, CD, NMR, MS, LCMS, etc. Thanks to IIT Tirupati for extending the spectroscopy and microscopy facilities for our needs during this period when we are acquiring all these. At present, our research capabilities are in the organic chemistry, synthesis and reactivity, inorganic chemistry, bioinorganic chemistry, theoretical and computational chemistry. But we would like to extend our scope to all other branches of chemistry and intensify the branches that we already have. So we would like to expand our infrastructure to suit the current needs, to tune our research, particularly to cater the fruit of our research to the society by collaborating and coordinating with the engineering and technology strengths that we have at IIT Tirupati. And that's what the strength we would like to use along with the chemistry. And we have our independent labs coming up in the main campus, which is the work of construction is going on quite quickly at the moment. And in 2022, we hope to be moving over there. So with this, once again, I welcome you all to this program of launching Masters in Chemistry at IIT Tirupati. A bird's eye view at the excitements and challenges in chemistry. I request all the students to to kindly listen to all the lectures and make use of that. Please tune to the program. Please bless all these new masters and PhD students and bless our program. Thank you very much for your participation. Thanks a lot. Rajiv.
Thank you, sir. Uh, Thank you for welcoming all the dignitaries and all of the participants, and also briefing us the chronological progress of the Department of Chemistry at IIT Tirupati. Yes. Now I request our Honorable Director, Professor K.N. Satyanarayana, to deliver the introductory remarks.
Thank you. Thank you, Professor Rao, for the opening remarks and giving an overview of where we have come so far from the beginning. I'd like to join him in welcoming all the eminent chemists who are there today, including Professor Balram and all others. It is Professor Rao's, shows Professor Rao's reach in terms of how he's able to pull together people to come and bless our program to get it started off on a very high note. And as he introduced, we are third generation IIT, and we've been mentored by IIT Madras. So when we started in 2015, we have initiated our activities from a transit, from a temporary facility which we hired, about a 61,000 square feet facility. And we were given, we had only 2 months to get the building modified, changed, It was not in a very great shape, and set up our labs. And with the help of CPWD and other organizations, in 2 months, we just transformed the whole building, got our classrooms ready, got our labs ready. We had decided the first semester we'll teach physics lab, so physics lab was ready. The chemistry lab was going to be taught in the second semester, so we had a little more time to get our chemistry lab ready, but we had it in all respects ready to get going. That was for the BTech program. And as mentioned by Professor Rao, we had a number of senior colleagues from IIT Madras coming and teaching the first 2 years, including Professor K.K. Bal Subramaniam, Professor Subramanian, Professor Sudhindra Rao, Professor Ranga Rao, Professor Mangal Sundar, very senior professors. So I think the first two batches felt they were very lucky to have been taught by this senior. And in fact, my colleagues at IIT Madras used to tell that they can't get these guys to teach them their first year students sometimes. And we've been lucky that our students were able to be taught by these very, very senior professors. And then what we did is, there are two departments I find a challenge in hiring faculty members. One is chemistry. The other end of the spectrum is statistics. With chemistry, the challenge is the large number of applicants. Okay, so it's a good challenge to have. It's a good problem to have, where you advertise, you get 800, 900 applications, and whatever criteria you put, you will come down to 150 or so. And then how do you bring it down to a reasonable number in terms of interviewing and so on? So that's the other end is statistics, where we don't even get applicants. And we have to keep searching for them. So in chemistry, what we did is, in the beginning, when we did the first round of recruitment in 2017, after I took over officially as the director, is to advertise for theoretical chemistry, because we knew we were going to take time to set up our laboratories, and it wouldn't be fair to bring in faculty members and not support them adequately in terms of the research. Whereas the theoretical chemists, you need to give them the computing facilities, because most of them were computational theoretical. We were planning to hire. So when we advertised, the first round, we took the theoretical chemists. Then we slowly started expanding in terms of hiring faculty members in the other area, organic, inorganic chemistry, that we recently hired. One of the models that we've been very happy and successful that IIT Tirupati is to bring in very senior faculty members at the beginning, so that they could mentor these areas. So we have 6 faculty members who retired from the IIT system, from IIT Madras, IIT Kanpur, IIT Bombay, who at this age of 65, when they retire, we got them re-employed. MHRD has been kind enough to understand that these new IITs need faculty members at senior level, and they permitted us to re-employ. In fact, they've sent out circulars to all other IITs, senior IITs, not to, that re-employment is cannot be done now. But in our case, as an exception, they gave us this opportunity, which has helped us immensely with the people coming in. So in chemistry, we were lucky to get Professor C.P. Rao. He was retiring, and through mutual contacts, we got to know that he will be willing to move. So I reached out to him, and he was gracious enough to accept our request and come here to get the program going. So we're going step by step, slowly. We don't want to rush through, but the thing is, we've been quite successful in our faculty hiring. We have 93 sanctioned positions for the institute, and we filled up all the 93 sanctioned positions. So we actually don't have a single opening today. But with the new batches joining, this new batch of students joining, we may, 1:10 ratio, we may be able to hire some more faculty members. And definitely chemistry is a department where we would probably be adding a couple of faculty members more in this coming year, because we have to distribute across 9 departments that we have. The other major advantage that IIT Tirupati has is the presence of IISER Tirupati. Both of us have a very common starting point. We had a common foundation stone laying program on March 28th between IIT, IISER, and IIT Sri City. And then our academic launch was the same week, 2 days apart or 3 days apart. We had our academic launch of our programs. And we've been working very closely from the beginning. So we have been, our faculty have been going and teaching there. Their faculty have been coming and teaching here. We've been working on sharing our resources effectively. And in fact, we have also started joint centers. Only 2 weeks back, we have inaugurated little over 2 weeks back, the Center for Atomic Molecular Optical Sciences and Technologies, which again, we had a number of eminent scientists from across the world come and bless that start of the initiative. And it was inaugurated by Dr. Abhinav Mitra, the scientific secretary in the office of the principal scientific advisor. And then we have seen people again. What we have seen is there's a critical mass of faculty in this area between the two institutes, so we joint center. Another initiative, joint center initiative that we are working on is on energy systems. Now, this is being again led by Dr. Vijay Mohan from IISER, so it's be a joint center between the two institutes. Even the way we procure equipment, especially the higher end equipment, we are trying to complement each other so that we can leverage the best what we could do. For example, and so as we are building our campus, as I told you, we had started off from a temporary campus where we completely rejigged the whole building, started an undergraduate chemistry lab, and then in the permanent campus, we quickly built up some facilities. In fact, I got a leaf of how to quickly build up from IISER Pune as to how they set up their lab, but we did it at a much bigger scale in terms of quickly creating this pre-engineered steel buildings. I myself a civil engineer, so I knew how to do these things quickly. And we set up reasonably large labs for the undergraduate engineering labs, that is mechanical, civil, electrical, and the workshop. And a few classrooms, hostels, and everything. And we managed to move all our classes into the permanent campus. Some of the classes in 2018, January, and all our classes from 2019 are from the permanent campus. We have built up classrooms, about a classroom building, and so on. All the most of the engineering labs are there, and we managed to shift, except the faculty and staff still operate on the temporary campus, but rest of our activities move to the permanent campus. We are in the process of building our main campus. Our campus is in a 548-acre site, a beautiful site with a mountain backdrop. Right now we have a 600 crore contract, which is under construction, where we are building 5 buildings in the academic area, including 2 department buildings, classroom complex, an administrative building, and a central instrumentation facility. So one of the first buildings I felt we should build is a proper central instrumentation facility, so that our faculty research can take off quickly. And this is a pretty large building. This is almost 50,000 square feet building just dedicated to central instrumentation facility. And we have the budgets lined up for equipping this based on the detailed project report that we have prepared. In fact, IIT Tirupati led the preparation of DPR for all the 6 new IITs, third generation IITs. And so we're confident we can equip this with top of the class equipment with the budgets that have been under the HEFA loan arrangement and so on. Our challenge has been the space. If you buy equipment, where are you going to put it? So I've been taking the stand with my colleagues that, you tell me how long. If you tell me it's going to take 6 months to procure the equipment, and you tell me that 6 months when we have the space ready, we order it. Otherwise, I've seen other institutions, new institutions, buy equipment, don't have space to put it, and sometimes before they open their boxes, the warranty period is over. So we've been a little, but we are very consciously doing this, but trying to get the best and going. So I see the other important thing that we're trying to, from the beginning, set up a culture is of interdisciplinary work between the various departments. People talk across departments and so on. So I'm very happy that the MSc program has been launched. We started off with our BTech program in 4 branches: civil, computer science engineering, electrical engineering, mechanical engineering in 2015. We started chemical engineering in 2018. Then we started our MSc Mathematics and Statistics in 2019. And this year we're starting our MSc in Physics and Chemistry. And definitely the program was very well needed, but we wanted a critical mass of faculty to be available before we start the program. So now that we have a critical mass, and also the confidence that we have a riser nearby to work with in case we need a class to be taken by someone else or our faculty go and teach there. And in fact, we want to match our academic calendar so that students should be able to easily go take classes across the campuses. So I'd like to join everyone in welcoming our new batch of MSc students. Our 14 students are joining. Hearty welcome to our campus. These are difficult times. All of us are going through this. We would have loved to welcome you physically, but then there are both two sides of the coin. I don't think we could have got all these eminent people to join in if I had to do it physically. Because we're doing it virtually, we could get all these people to come and join. So we have to leverage what is possible in the current situation. So this semester will be completely online. All IITs have taken this route of this current semester being online. So because it's going to be online and you need to get used to the IIT system and so on, we have recommended that the first semester go a little bit easy, limit to about 12 to 14 credits. Online course, because over the four semester period and the vacation in between, we could make up the couple of classes probably that you're not able to take now. So that this is challenging way to do it. We don't know how this pandemic is going to go. Right now, our institute is also facing the brunt of the pandemic. That's why we don't want the students to come here. I myself have just got out of my quarantine after testing positive. And similarly, a few other faculty members have tested positive. That's the staff members have tested positive. So my request to the students is to stay safe this semester. And I'm hoping that by November or so, if we are able to get things under control and we have all our act together, we will try to start getting you in, and maybe finally you can come in and take the exams, and then we'll continue the next semester. That's our hope. Every day situation changes. We're all dynamic. Every day we have to keep taking decisions. So under the current circumstances, I think this is the best way to take things forward. So once again, I would like to congratulate my colleagues in getting this program off the ground. I have only one advice to the students. This is something that I've been, especially the science departments, I've been trying to force them to open up their coursework so the students use the advantage of our engineering departments here for the students to go and take at least one or two courses in the engineering domain, in the application domain, so they get more exposure. So I've been trying to make them, everyone, all the departments I feel that they have to learn this. If they're getting an MSc from here, they will do this 20 courses, and they've been very reluctant to let the students go wander out and explore other things. So I'm glad that they have given the option of at least 2 free electives to the students. In fact, this is something that I have to push it down, and I find that they have, I think, a couple of department electives. So my suggestion to the incoming MSc students is to go out of your narrow domain, reach out. World is more interdisciplinary today. Things are, it's not just very narrow. So go venture out and take courses, maybe even in humanities or in other engineering departments, at least 1 or 2 courses. That would be my suggestion and appeal to all of you, so that we reach out and make this people look beyond their narrow confines. With that, thank you very much, and I will once again thank all the esteemed guests for accepting our invitation and joining. Thank you.
Thank you, sir. Thank you for your encouragement and taking us through the growing journey of IIT Tirupati. Due to the time constraint, I shall be introducing our dignitaries briefly, and I might be missing many notable achievements of all of the speakers. I seek their humble apology in this regard. I request all the participants to visit their homepage and to get complete information about them and their research accomplishments. Now let me move to the main program. It is our matter of pride that to formally inaugurate the master's program, we have with us Padma Bhushan Professor P. Balaram. He is the former director of Indian Institute of Science, Bangalore, present faculty of chemical ecology at National Center for Biological Sciences, Bangalore. Professor Balaram has achieved many distinguished accolades. To name a few, Shanti Swarup Bhatnagar Prize by CSIR, G.D. Birla Award for Scientific Research, the World Academy of Sciences Award in Chemistry, the Padma Shri, Padma Bhushan by Government of India, and many more. He is a fellow of Indian Academy of Sciences, Indian National Science Academy, and the World Academy of Sciences. He has contributed significantly in the field of biochemistry and molecular biophysics. Now I request Professor Balaram to formally inaugurate MSc program and enrich with us with his experience in the inaugural address. Professor Balaram, sir.
Can you see my screen?
Yes.
Yes, sir.
Yes, you can.
Yes. Yes.
The task that Professor Pullarao has given me is to make incoming MSc students enthusiastic about chemistry. I think there's no better way of doing this than to quote from the Prime Minister after he won the last general elections, where he said that chemistry defeated arithmetic in the 2019 polls. This immediately tells you that it is important to study chemistry irrespective of the profession into which you are going. Now, for me, it is a pleasure to be able to participate in the inauguration of the first batch of an MSc chemistry course in an IIT. Some 53 years ago, I was also a student of an MSc course in one of what are now called the first generation IITs, but then they were not far different from what IIT Tirupati is today. Now, the importance of chemistry need not be overstated. You know, Galileo a long time ago said mathematics is the language with which God wrote the universe. Today, we might paraphrase this to say that chemistry is the language with which nature wrote the book of life. So almost everything that you have in life can be understood in terms of chemistry. The importance of chemistry as a bridging subject between biology and medicine was emphasized by the famous biochemist Arthur Kornberg. He, in fact, discovered the enzyme DNA polymerase and fired what I think is the first shot of the biotechnology revolution. He said that chemistry is the lingua franca of the medical and biological sciences. And I don't think anybody can say this any better. This tells you that if you're going to be a biologist or if you're going to be a physician in later life, it is very important to have an understanding of chemistry. I found this cartoon on the website of a Western university. And there's this man trying to do a crossword puzzle. And he asks the lady who's sitting next to him, what's a 9-letter word for biotechnology? And she promptly answers chemistry. Now, of course, for all the students who are here, I would pose to you the question, what is a 9-letter word for material science? The science of materials now is very important. It's very important in engineering. Much of the inroads that engineering has made into medicine really depend on advances that have taken place in material science one way or the other. And a great deal of the interface between physics, engineering, and chemistry lies in the area of material science. But we are all in the situation that we are today because of the coronavirus. There is nobody who hasn't heard of the word coronavirus. It's a public health nightmare, and an artist's delight. So I've simply put together a set of pictures from the internet. And one definition of a virus, which I would show you on my next slide, is that it's a piece of bad news wrapped up in a protein. Now look at the coronavirus. It's really excited the imagination of people everywhere, policemen, particularly in India. And in Europe, it's attracted the attention of chefs. In Italy and France, which were severely affected, Easter eggs and cakes have now been made which resemble the coronavirus. Everybody can recognize coronavirus. But what is a virus? And I have taken this from a philosophical dictionary of biology by the famous biologist Peter Medawar. He wrote this book called Aristotle to Zoos. And then he took each letter in the English alphabet and took some words from biology and wrote a page on them. And he talked about viruses. He says, no virus is known to do good. It has been well said that a virus is a piece of bad news wrapped up in a protein. What is the bad news? It's the genetic material, which is the RNA. What is the RNA? It's a chemical. What's the protein? It's another chemical. So there's chemistry everywhere. Are viruses living? Viruses are truly non-living. Viruses can be crystalline. They can be crystalline just like any other chemical material. Many crystal structures of viruses have been determined. But at the same time, when a virus infects a cell, it causes all the terrible things that are happening today. Now, I speak this from experience. Professor Satyanarayana has said that he's tested positive. I not only tested positive, but I went into hospital for 10 days and then was in quarantine for 14 more, and I've come out of it. And you can see that I have recovered from the virus, and hopefully so will everyone else who is infected with the virus. Now, chemistry and biology are very closely related, as are chemistry and material science. And many times they are related because of their differences in length scales, in time scales, and in energy scales. Irrespective of the science that you're studying, whether it's physics, chemistry, biology, or engineering, it's important to have an idea of length scales, time scales, and energy scales, because the world works with these three quantities. They work in dimensions of scale, length, and time, and energy. And now you can see where a virus is placed. A virus is placed somewhere between the ribosome. The ribosome is the structure which was determined by Venki Ramakrishnan, for which he got the Nobel Prize. And mitochondria, which are inside cells which produce energy by means of chemical reactions. But you can see it's a continuum. It's a continuum from the CC bond in ethylene to glucose to hemoglobin to the ribosome to the virus and so on. So chemistry moves seamlessly into biology. When Pullarao asked me to give these brief remarks, I wondered, what can I say about chemistry? Most of the distinguished chemists who are assembled here might actually think of me as someone who defected to the discipline of biology, because right from day one, I had an appointment in the Biological Sciences Division of the Indian Institute of Science. So I went back and asked, what would be the foundational pillars of chemistry? This is what you must learn well in your MSc course. You will rarely learn this afterwards. This is the last chance. Mendeleev, of course, because he gave us the periodic table. I will come to that in a moment. Wohler, because he did the synthesis of urea from ammonium cyanate. Although this was not the decisive evidence against vitalism, Wohler's synthesis of urea at least bridged what we today call inorganic and organic chemistry. An organic molecule appeared from what was considered an entirely inorganic substance. Your director has already talked about the importance of interdisciplinarity. I think it is extraordinarily important today for students not to listen to what their professors say, but also to read well beyond what their professors say. I think the only purpose of education is to teach you how to read, how to acquire knowledge, not to listen to what is told to you only in the classroom. Boltzmann. It is because of Boltzmann that we really got these ideas of dynamics. We've got the idea of the atom. And if you go back and read about Boltzmann, a physicist, in those days everybody was a natural scientist. In the middle of the 19th century, thinking about heat, for example, he came up with the idea of atoms. I'll come to that in a moment. Pasteur, of course, gave us the idea of structure before Van 't Hoff and Labelle, because when he resolved the tartaric acids and got the connection between optical activity and two forms of the same molecule, DNL, tartaric acid, rotating the planes of polarized light in opposite direction, he had established a profound principle that the structures of molecule influence their physical properties. Now, look at Mendeleev's periodic table. Whether you want technology, I don't think any engineering can be done without many of the chemicals that are elements that I have colored yellow. Organic chemistry are the elements that I have colored, and biochemistry with light green. But then in light pink, I have all those metal atoms which are the subject of inorganic chemistry. But without them, there is no life. But the literature is moving very fast. I have not colored tungsten as an important element in biochemistry. But today, tungsten is a very important element in biochemistry. This is an old slide. And I think the technological uses for the other elements are going to be found. So what did Mendeleev give us? Mendeleev gave us the idea of diversity in chemistry. This is what Mendeleev looked like. And there's this wonderful book called Uncle Tungsten, Memories of a Chemical Boyhood, by a very prominent neurologist who was a wonderful writer. And he talks about, I spend hours now enchanted, totally absorbed, wandering, making discoveries in the enchanted garden of Mendeleev. Therefore, when you have the periodic table hanging in those labs, and I hope Professor C.P. Rao will now hang one very large periodic table in that very large room which he showed us. This is what Wohler did. All he did was heat ammonium cyanide and he got urea. Urea today is so important as a fertilizer. But where is urea produced? In the kidneys. And he wrote in a letter to Berzelius in 1828 that in a manner of speaking, I can no longer hold my chemical water. Later on, this has been, water has been replaced as urine. I must tell you that I can make urea without the use of kidneys of any animal, be it man or dog. This was the first shot, really. We knew that there was a subject to come, that was biochemistry. But that would come many years later, as you will see as I go along. Pasteur gave us this idea of stereochemistry, optical activity. He also was a biologist because he gave us microbiology and the vaccines. Pasteur probably represents the iconic scientist who did not only wonderful basic research, the foundations of stereochemistry, but also wonderful applied research giving you vaccines. Today, everybody is interested in vaccines. He was also one of the scientists who introduced the idea of doing experiments and observation. And the famous dictum is due to him: chance favors the prepared mind. This means that the more experiments you do, the more likely you are to stumble upon something. So this is why you must spend more time in the laboratories. When you spend more time, chemistry is an experimental science. Although many of my theoretician friends who are there in the audience will tell you you can do many things on the computer, but there is nothing like doing something in the laboratory. It is an experimental science. This is fermentation. All of you know sucrose ferments, grape juice, for example, goes to ethyl alcohol and carbon dioxide. Many of the most senior chemists here know the virtues of ethyl alcohol. And you will see here that alcohol fermentation could have been solved, and this is Kornberg, by any of the great chemists of the 19th century. Berzelius, Liebig, Wohler, all of them might have succeeded, except for their neglect of biology and their failure to recognize the central role of yeast in fermentation. Then he adds, Pasteur, an equally great chemist, did appreciate the role of yeast, but his exaggerated immersion in biology caused him to neglect his chemical roots and miss discovering that enzymes are the vital force of fermentation. Edward Buchner had to do this. Buchner of the famous Buchner funnel had to do this in 1896 when biochemistry was born. Boltzmann, look at Boltzmann. Jacob Bronowski, in his famous BBC series, The Ascent of Man, pays this major tribute to Boltzmann. In Vienna, at Boltzmann's grave, there is the tombstone. where you have his famous equation S is equal to K log W inscribed. What did Boltzmann do? And he says, to whom more than anyone else, we owe the fact that the atom, the world within a world, is as real to us now as our own world. What was Boltzmann thinking about? He was thinking about heat. Heat is a subject of physics. And he realized that heat is a random motion of atoms. And when energy is degraded, said Boltzmann, it is the atoms that assume a more disorderly state. Entropy is a measure of that disorder. Statistical thermodynamics descends from Boltzmann. And that is sometimes at the heart of physical chemistry. In my very last slide, I will show you the importance of atoms. No one in the 19th century, it was said by physicists, that the only people who believed in atoms were chemists because they were trying to build pictures of molecules, and they called these images sensorial images which can have no reality. Atomic physics was to be born only in the early decades of the 20th century. So in the mid-19th century, atoms were a figment of imagination. Atoms had descended from the thought of ancient civilizations, but it was not really known what they were. Richard Feynman, in his famous lectures on physics at Caltech, writes this in his very first chapter. He says, if in some cataclysm all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? And he answers his question. I believe it is the atomic hypothesis or the atomic fact or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. And you can clearly see the Van der Waals force now coming into being in Feynman's lecture. Now, atoms are central to chemistry. Molecules are chemistry. And therefore, I think you must take pride in the discipline that you are going to study, that chemistry truly now impacts every discipline that you see around you. And in concluding, I would just like to remind you of one fact. Some years ago, the Bombay High Court, in a famous judgment, declared in 2010 that steam is not a chemical for taxation purposes. Now, it turned out that immediately after this judgment came down, the Royal Society of Chemistry in England put out a challenge. It asked anybody who brought them a sample of a material which was non-chemical, they would give them £1 million. And every one of you who's a student today can look around you and ask, is there anything around you, including yourselves, which is not made up of chemicals? Can there be a more important facet of chemistry than this to understand? I hope in the 2 years that you have your course, you will not only be excited by chemistry, you will also be challenged by chemistry, and some of you will in later life have the opportunity to make discoveries in chemistry. Thank you very much and good luck.
Thank you, Professor. So may I request you now to just formally inaugurate the program. I will just show the slides which our colleague has prepared. Yeah. Okay. So may I request you, sir, to give me the permission on behalf of you. I will put the slideshow.
Go ahead.
Okay, sir. Yeah. Okay. Thank you, sir. Thank you for joining with us.
Thank you.
And thank you for the excellent speech. Yes, thank you for the excellent speech and the advices. I'm sure that the advices will be extremely useful, not only for the students, for all of us. Let me move forward. So our next speaker is the former founder director of IISER Mohali and honorary professor JNCSR Bangalore, Professor N. Sattamurthy. The eminent theoretical chemist has received several distinguished awards. To list a few: Young Scientist Medal by INSA, Young Associate of Indian Academy of Sciences, Alexander von Humboldt Fellow by Max Planck Institute, Göttingen, Germany, Shanti Swarup Bhatnagar Prize by CSIR, Reverend Father Edanapalli Memorial Award by Indian Chemical Society, Sir C.V. Raman Award by Hari Om Ashram Trust, UGC, Silver Medal by Chemical Research Society of India, J.C. Bose Fellowship by Department of Science and Technology, and many more. He is the fellow of the Indian Academy of Science, Indian National Science Academy, and the World Academy of Sciences. Now I request Professor Sattamurthy to educate us with his experience about the challenges and excitements in the world of chemistry. Sir, I will put the slideshow on.
Yeah. So can you see the screen?
Okay, okay. So please go ahead, sir. Right now it is not yet visible.
I'm on my first slide.
You have to go to the Zoom and share screen, sir.
That's what
Again, you have to
yeah,
repeat the same exercise as we have done last time.
I go to Zoom. Where do I find the shared screen?
Bottom, sir, green upside arrow on Zoom screen.
At the bottom, Shakti.
Yeah,
you
got
see
it.
Okay.
Yeah. See, I need a Roma experimentalist to help me. Yeah. Not bad.
Yes. Now you can put the slideshow on. It is visible now, sir, your window.
Now my window is visible?
Yes, sir.
Okay, except that I'm not able to see it.
You can see all your emails. Yeah, now the screen is up. Yeah.
Yeah.
Okay. Yeah, so we are on the first slide, sir. Please go ahead, sir. Thank you.
Okay. Well, it's a disadvantage to talk after Professor Balram, and he, is very, very difficult. So he puts me at a disadvantage. If what he spoke is all relevant to chemistry and life, I would take you to the other extreme. And that is to wonder about the first chemical bond in the universe. Your director mentioned about the world, your head of the department talked about the world, Balram talked about life. But I've been curious to find out how the first chemical bond was formed or when it was formed. If we ask the question, what is the first molecule that was formed, in all likelihood, many of you would say it was H2 molecule. Those of us who are theoretically inclined would perhaps say H2 plus, that is the hydrogen molecule ion. It turns out, actually, if you had asked me this question a few years ago, I would have said H2. If you pressed me hard, I would have said H2 plus. But today I understand that was really a helium H plus that was formed first in the universe. That is, it's a covalent bond, if I can call that, a pair of electrons shared by two nuclei, a formal definition of a chemical bond introduced by G.N. Lewis in 1916. Very recently, this species was detected in the planetary nebula, NGC 7027 is the number for it. You can see it was recently, means just about a year ago. And this is from a very young planetary nebula and very small in the astronomical scale. But the nebulae are the remnants of stars which came after the universe. This is what I understand from my physics friends. So I got curious to find out how all these things happened. So I learned from Gamow's book that in the beginning it was all radiation. He quotes the Bible, God said, let there be light. Then Gamow says, what is the meaning of creation? He gives the English explanation. making something shapely out of shapelessness. So until an atom was formed, or even the particles were formed, there was perhaps radiation, or what could be called the radiation. With Einstein's formula giving you relationship between mass and energy, you can go from the left side to the right side, and the particles, protons, neutrons, electrons were formed. And then came the atoms. So if you want to call whatever happened up to that point, it was all physics. And it's all over in 3 minutes, according to astrophysicists, after the Big Bang. If you ask me to define what is the Big Bang, I will not be able to tell you what it is. All I will understand is that it was a unique instance, a singularity to be called mathematically. And the way astrophysicists look at, cosmologists look at the universe, they look backwards all the time. Where you are now, you go back and see how the universe evolved. And the ratio is, formula is given. The radius of the universe goes as 1 over 1 plus z, which means if you go back in time, measured in the form of a redshift, leave it to Umapati to explain to you at some point what is a redshift. And that gives you an idea how things were in the past. Today, the cosmologists tell us the background radiation is 2.7 Kelvin. So you can work backwards at Z equal, redshift equal to 1000, the temperature at that time when the atoms were being formed, where you were able to distinguish matter from radiation, the temperature was of the order of 3 to 4000. Since you know the surface of sun has a 4 to 5000 Kelvin temperature, it gives you an idea of the kind of temperature that we had. You can look up the density of matter that was there at that time. Today, the universe, in the universe, apparently there are 10 to the power minus 6 hydrogen atom per cc. It was 9 order of magnitude larger at that time. But what is important for us chemists, students who have joined the MSc program, is to recollect from their thermodynamics course that if there was expansion, because the universe was expanding after the Big Bang and it continues to expand, and it is considered adiabatic expansion. If you recollect your adiabatic expansion, that means there would be cooling. And this cooling is very important for atoms to be formed, for molecules to be formed. And then if you ask the question, which was the first atom to be formed, it turned out it is not hydrogen. It was helium atom that was formed. In the nucleosynthesis, only 3 nuclei were formed. There are protons which led to alpha particle formation and lithium nucleus formation. And this meant there was helium atom formed, and then a hydrogen atom formed, and then lithium atom formed. It was in that order of decreasing energy release, which also seemed to be the chronological order in which the atoms were formed. And here is the abundance. Hydrogen, if you take as 1, helium is 0.1, and lithium is 10 to the power minus 10. Then I'm sure you would immediately ask, how about the other elements? They were not anywhere in the picture. They came much later after the stars were formed. Astrophysics people tell us that it was iron that was formed. And how about the remaining rest of the periodic table that Professor Balram referred to? That story is even more complicated or even more strange. But we are not going to go into that. Coming back to this first chemical bond, I understand from what the astrophysics people tell me, it was a helium neutral which combined with a plenty of proton around to form the first helium H plus species. It's ionic, diatomic, molecular ion by releasing energy. This is what is called radiative association. 2 particles come together, emit light, and form a molecule. Now, Professor Balram emphasized on the need for doing experiments. As early as 1925, one of the early mass spectrographs taken showed the existence of mass by a charge equal to 5. And it was interpreted to be helium H plus as early as 1925. Now, Umapati will say, look, I need to look at a spectrum For him, the infrared spectrum of helium H plus was recorded by none other than Hertzberg in 1978. And our astrophysics friends are looking all around in the interstellar medium for helium H plus. Finally, last year they detected, and helium H plus was detected. But I told you that the planetary nebula came much later, something like 12, 13 billion years later. So seeing helium H plus here is not an evidence that it was formed after 3 minutes of the universe, but we will leave that for the astrophysicists to figure out. There are two different ways of forming helium H plus. One is from the helium neutral and a proton, other is from a helium ion and a hydrogen atom to give the same species. If there are two ways of forming helium H plus, there are several ways of destroying. And it is a useful destruction. The helium H plus could combine with hydrogen atom and give you hydrogen H2 plus. This is an exchange reaction. The proton here goes over to hydrogen, forms H2 plus. And if you look at the reverse reaction, chemists learn principle of microscopic reversibility, the principle of detailed balance. For our own reasons, we are always looking at the reverse reaction, and we have spent 40 years of studying the reverse reaction at IIT Kanpur. That tells you that you can spend your lifetime looking at an elementary chemical reaction which presumably has no practical use, at least as far as we can tell. Earlier people thought in 1951 it is a hydrogen atom and a proton which would form H2 plus, first molecule to be formed. It turns out that is not true. Our own Chandrasekhar, the Nobel laureate Chandrasekhar, of whom we hear a lot, he studied the formation of H minus. A hydrogen atom can take up an electron and form H minus. Not a simple process. Again, it has to take place by radiative attachment. And this H minus can combine with the hydrogen atom and give you H2 minus. So this is called an associative detachment. That is, these two come together and the H2 minus loses its electron and forms hydrogen molecule. So the hydrogen molecule could be formed from H2 plus, or hydrogen molecule could be formed from H2 minus. Many chemists, including myself, I used to teach my students H and H come together and form H2. Don't believe them. Don't believe me. H2 is not formed that easily. Definitely not in the lab, definitely not in the early time of the universe. It is really the potential, and here is the potential energy curve for H2 minus. It crosses with the H2. So here H2 minus is an independent entity, but when it comes over here, it loses electron and becomes hydrogen molecule. A student of mine worked on this curve for 3 years, and all he could do at the end of it was publish a simple paper showing how this curve crosses with the neutral H2 molecule. This is just a picture of Orion Nebula, which contains plenty of hydrogen molecule. Having said that H2 molecule is to be formed from H2 minus, somebody I know, Urena, his name is not listed here, is one of the senior authors here, in 2015, decided to form H2 minus in the lab. It is not very easy. You can form H2 minus in a highly excited rotational state and then knock an electron off to form hydrogen molecule. And if you look at the photo detachment process, there's a lot of oscillations. Till this date, this oscillation remains unexplained. Without knowing these oscillations, I asked an undergraduate student in IISER Mohali to look at the problem and calculate the cross-section for H2 minus to become H2. This is the curve that he got. You don't see any oscillation here. You see a hump here and then a little dip here. That's all that you get. You don't get the kind of oscillation that was determined in the lab. And we still haven't published the paper. I don't know how the referee would react to it, but the fact remains that it remains unexplained. After H2 plus, helium H plus, what happened? You can have at least two different channels. You could form H3 plus. The first triatomic species to be detected in the interstellar media. Just now means a few days ago, we got a paper accepted in molecular physics This was a paper we published with great difficulty after struggling with referee for 1 year, where we proposed that these species, the helium atom I told you, H atom I told you, proton I told you, these three could come together and form helium H2 plus, and it can lead to helium H plus. So now this paper is formally accepted, and I must tell you that this species was detected in the lab at the same time helium H plus was detected in 1925 using mass spectrometry. They found a M by E signal of 6 for helium H2 plus, 5 for helium H plus. So it's almost 100 years later that we are proposing a mechanism for helium H2 plus formation and then subsequently helium H plus formation. Now, what is the take home message? You had this grand vision from Professor Balram, how biology and chemistry could work together and understand life and everything that matters for life. Here I have gone to the other extreme and told you how simple species like H2 can remain a puzzle. The formation of helium H plus and its destruction. I talked about thermodynamics, now I am talking about kinetics. Without these two, there is no physical chemistry. So the kinetics of the formation and destruction of helium H plus in the early universe remains to be understood. There is enough room for every one of you to look into this puzzle and solve it. So with this set of slides, I want to welcome you to the world of chemistry. And there is so much to discover and so much to understand. The choice is yours. You can choose a simple elementary chemical reaction, or you can look at a complex biological process. It is your choice. Do whatever you want to enjoy. All the best to all of you. Thank you.
Thank you, Professor. Thank you for taking us through the history of fast chemical bond and showing us how fascinating the subject is. Thank you once again. So, sir, may I request you to stop sharing on your Zoom window? Yes. On the top, you will see a red thing. Yeah, it is done. Thank you, sir. Thank you. Yes. So, our next speaker is Professor V. Chandrasekhar, the present director of TIFR Hyderabad. Professor Chandrasekhar has received many accolades, which includes the Shanti Sharup Bhatnagar Award, Frederick William Bessel Award of the Alexander von Humboldt Foundation, Homi Bhabha Fellowship for Excellence in Research, CRSI Medal, Indian National Science Academy Young Scientist Medal, Indian National Science Academy Golden Jubilee Medal, Shastra C.N.R. Rao Award, J.C. Bose National Fellow by DST, Lalit Kapoor Chair Professorship at IIT Kanpur. He is also the former director of NISER Bhubaneswar. He is the Fellow of Indian Academy of Sciences, the Indian National Science Academy, the National Academy of Sciences Allahabad, the Academy of Developing World, Trieste, Italy. He has significantly contributed in the area of organometallic chemistry and other allied topics. Now I request Professor Chandrasekhar to enrich us with his experiences and tell us about the excitements and challenges he has found in his area. Professor Chandrasekhar.
Thank you very much, and thanks a lot for making me a part of this wonderful occasion of the inauguration of the MSc program. So I thought I will use this occasion to tell you a small story, and the story has to do with the recent Nobel Prize in Chemistry, which has been given to two people. And the inspiration that I would like myself and other people and the young students particularly to draw is the fact that one of the Nobel laureates was 97 years old when he got the Nobel Prize, John B. Goodenough. Of course, as many of you might be knowing, apart from doing excellent work, one of the criteria for getting the Nobel Prize is that you have to be alive. So John B. Goodenough did consistently good work for a very, very long period and was alive to receive this Nobel Prize last December. And I thought I will just share with you about this particular person, which should serve as an inspiration for not just chemists, for actually everybody. So the Nobel Prize in Chemistry in 2019, as many of you might be knowing, particularly I hope the young students know, has been given for something that we use almost everywhere, in our cell phones, in our laptops, and many other devices. And this is for the development of the lithium-ion batteries. There are three people: John B. Goodenough, who is currently at the University of Texas, Austin; Stanley Whittingham, who is at the Binghamton University, SUNY, that is the State University of New York; and Akira Yoshino, who is at the Meijo University.
Chandrasekhar, your slides are not moving. And also, if you can, go to the slideshow mode, it will be better.
Yeah.
Okay.
Slideshow.
Can you? This is the first slide. Is it visible?
Yeah. Go to the next one, which you are explaining.
It is visible, sir, but it is not in the slideshow mode.
It's okay. Let me see. It says here slideshow.
Yeah, that hourglass.
Yeah. That's right. Okay, let me stop the sharing and again restart it. Let me see if that works.
Yes, sir.
Yeah.
It's working now.
Okay. So these three people, this is John B. Goodenough, Stanley Whittingham, and Akira Yoshino, are the people who have been credited for the development of the lithium-ion batteries. And I'll be speaking particularly about John B. Goodenough because he's a remarkable person who has traversed areas from physics, from random access memory, from magnetism to batteries. And he continues to work every single day. Even today, there was an interview of him after he got the Nobel Prize and more recently, and he continues to go to the office every single day and work. I don't know post-COVID what he's doing, but certainly pre-COVID, he was in the office every single day. Now, why was this work important? It actually, there's no really need to tell why this work is important because all of us are using this work in our daily lives. And I would strongly urge the young students to go through the original sites for getting more information. The first is a summary, advanced as well as for lay people about the Nobel Prize. And for the Nobel lectures themselves, there's a fantastic lectures available of these three people on YouTube. And 3 lectures I've given these sites over here. So please do visit these URLs and check out for yourself what these lectures, how they explain their own discoveries. So the reason, and let's go to John Goodenough. He was born in 1922 in Jena, Germany. And at 97, he is the oldest person to win the Nobel Prize. He has worked at several institutions, obviously. He was at MIT. He was heading the inorganic chemistry department at Oxford University. And then he has moved to University of Texas after his retirement at Oxford and has been there for a very, very long time. And he has worked along with other people on this problem of lithium-ion batteries. And the problem stems from mankind's need to have portable energy. Wherever you go, if you have the access to energy, then you're not stuck to a particular place. So the idea of using lithium metal in batteries was an old one. And the advantages of lithium is the fact that it is very lightweight. And also it can be ionized very readily. So initial efforts were on using the lithium metal itself as one of the electrodes. But this has run into several problems, including what is known as the dendritic problem. The lithium ions which come back and deposit on the lithium metal project into dendritic shapes, and they pierce the interface between the anode and the cathode and causing accidents. So this led to the thought that can we use lithium ions on both the electrode materials where the lithium ions are migrating from one to the other and the electrons are passing in the circuit. So these are what is known as the sort of batteries that we currently use in our systems. So the battery structure is somewhat like this. You have, this is the version that is the Yoshino battery, where you have the petroleum coke on one side and you have the cobalt oxide on the other side. Now, the materials that are involved in this, Professor Balram has spoken about how chemistry is very, very deeply interconnected with other areas of research, material science, biology, and this is an area where chemistry is very strongly connected with material science, energy materials. As Professor Satyanarayana was mentioning, Professor Vijay Mohanan is one of the leading experts in this area in the country, and it's very nice that IIT Tirupati can actually have access to his knowledge regarding these types of materials. So here you have two electrodes. You have the petroleum coke based electrode, which Yoshino had discovered. And of course, now there are graphite based electrodes. Essentially, this also tells you about the versatility of carbon. Carbon, which can come in various forms. And one of these forms where here it can intercalate lithium ions. And you have cobalt oxide, which can also intercalate lithium ions. So the contribution of good enough is towards this cathode material, the cobalt oxide material. Over a period of several decades, Goodenough and his colleagues have come up with a material which can intercalate lithium ions. So from the anode, for example, as oxidation occurs and you have lithium ions going through the separator and the electrolyte, they go towards the cathode and they are deposited in the cobalt oxide, and the electrons are traveling in the external circuit, which can be harnessed for various purposes. This is what happens in the discharge cycle. In the charging cycle, you have exactly the opposite, where you have electricity from the outside and you have the lithium ions coming towards the petroleum coke or the carbonaceous material. So the three people who have worked on it, particularly John Goodenough, has done enormous work towards this cathode material, and it is for this particular development that he has been awarded the Nobel Prize. The essential reactions are very simple. So you have the reactions, which is the carbon material, which has got lithium. So you have a lithium plus coming out of it and the electron. And this lithium plus goes through the membrane and goes through the electrolyte and forms LiCOO2. So this is during the discharge cycle. And in the charging cycle, you have exactly the opposite. And the beauty of this particular technology that has been developed is, with this, the potential of these batteries has been increased nearly 100%. So now we have about 4-volt batteries that are available, and these are accessible to everybody as a form of chargeable batteries, which all of us use in our devices. And of course, further, Goodenough has not stopped with this lithium cobalt oxide materials. Several new materials have been developed by him and his group, which includes phosphate materials of cobalt as well as iron, which are being used. So I thought I will share with you a very short summary of this recent Nobel Prize, with showing you that how persistent work in an area of importance can lead to a great benefit to humanity, which this particular work has clearly demonstrated, and B, where age is no barrier for creativity. And John Goodenough has shown that by working continuously over several years, and even at the age of 98 now, he continues to push the barriers in science and technology for the benefit of humankind. Thank you very much.
Thank you, Professor. Thank you for telling us a wonderful story and the appreciative words. So now we have as a next speaker, Professor S. Umapati, Present Director, IIT Bhopal, Professor of Department of Inorganic and Physical Chemistry and Department of Instrumentation and Applied Physics at IISc Bangalore. Professor Umapati has received several accolades, which includes Young Investigator Awards from University of South Carolina, Sarna Jayanti Young Scientist Award by Government of India, Sir C.V. Raman Young Scientist Award by Government of Karnataka, CRSI Bronze Medal, Santi Swarup Bhatnagar Award by CSIR, J.C. Bose Fellowship by Department of Science and Technology, and many more. He is the J.W.T. Jones Fellow of the Royal Society of Chemistry, London. He is also the Fellow of Indian Academy of Sciences. He has worked significantly in the area of molecular dynamics using Raman spectroscopy. I request Professor Umapati to share his experience and tell us few words to our new students. Professor Umapati.
Okay, thank you very much. Let me thank Dr. Pularao and of course the director for inviting me to speak on this occasion. I would like to broadly say that, what Balram and Satya and of course VC also has mentioned, that in today's science, today's chemistry is more interdisciplinary than ever before. Of course, coming from my field of expertise and what I have learned in the last 20, 30 years is one of the biggest weaknesses in chemistry is quantitativeness and also ability to use instruments with its fullest capacity. I think in India, we have been not so fortunate to get trained in high-end instrumentation. And not only that, we get very little training on utilizing an instrument to its best of its capacity, in spite of having spent large amount of money. And that requires places like IITs, which are offering a master's degree, incorporating an instrumentation, basic concepts of instrumentation. Therefore, the students are not afraid of using high-tech instruments. And also a course on artificial intelligence and data analytics, which are an extremely important part of the future of chemistry. Chemistry is not anymore about synthesizing some molecules. It's also about developing devices based on materials you make, or maybe developing drugs towards diseases. So we have to move away from being traditional synthetic chemistry to functional chemistry and delivery of chemistry to society. Now we have, for example, I'm very glad to hear Dr. Satyanarayana mentioned about starting an optical center. We have started one center for photonic science and engineering, encompassing applications of light from medicine to optical communication in the middle spectroscopy. And all of them have to translate into some kind of technology in the years to come. As you have seen what VC mentioned, its creativity has nothing to do with the age, but it's a lot to do with the ability to take risk and depth of knowledge and breadth of knowledge. As the future of the world depends on high-tech instrumentation and innovation and also a considerable amount of data analytics. So it's becoming more and more quantitative and mathematical, in addition to being a lot more physics and engineering involved. And I hope that this MSc program that is started at IITs will help in accelerating the students' breadth of knowledge in addition to depth of knowledge in chemistry and physics and engineering. So I wish all the best to all the students, and I hope they will become the new trendsetters in chemical research, unlike what we have been doing in India. As you can see, even today, physical chemistry or chemical physics does not even have an independent committee in Delhi. I mean, they are all part of inorganic chemistry. And soon they will probably become part of organic chemistry. And so that's the thing we should try to avoid in the future. Thank you very much.
Thank you, Professor. Thank you, Professor Omapati, for reminding us the necessity of the interdisciplinary work in chemistry. Before I move to the next speaker, I would like to thank Professor Sandeep Verma. He has to leave a little earlier because he has another important meeting to attend. He conveyed the best wishes to our students, and he tell us that he will be joining in future in some other program to address in front of our students. So I thank once again to Professor Sandeep Verma. So our next speaker is Professor J.N. Murthy, the present director of IIT Tirupati. Professor Murthy has served as Lalit Mohan Kapur Chair Professor and Dr. Jagmohan Garg Chair Professor at IIT Kanpur. He has received many distinguished awards. To name a few, Young Chemist Award from Chemical Research Society of India, Ramanna Research Fellowship from Department of Science and Technology, India, Shanti Sharup Bhatnagar Prize from CSIR, J.C. Bose Fellowship by Department of Science and Technology. He has also received the Bronze Medal from Chemical Research Society of India and many others. He is a Fellow of the Indian Academy of Sciences, Fellow of Royal Society of Chemistry, Fellow of the International Center of Transdisciplinary Studies, Jacob University, Germany. He has contributed significantly in the area of organic photochemistry and the allied topics. I request Professor Murthy to share his experience and say a few words in front of our newly joined master students. Professor Murthy.
Hello. Hello.
Yeah, yeah, we are able to.
Hello.
Yes, yes, we are able to hear you.
Yeah. Okay. I think I'm sorry that I have just pulled to a side on the highway, and
Hope we
well,
are.
there is a kind of instability with the connection, so you'll have to bear with me. Well, I didn't want to give a lecture. I mean, talk for about 10 minutes on the science that I pursue or chemistry that is exciting. Rather, I've been teaching master students and PhD students for well over 20, 21 years. At IIT Kanpur, one of the pioneers for master's education, particularly in chemistry, very, very, very renowned. The legacy left behind by the likes of Professor Sena Rao, Professor Mehta, and everybody that you have here. I think everybody has an origin to, when you talk about the chemistry to IIT Kanpur. I think it's a great occasion for IIT Tirupati in general and the department in particular to start off with this MSc in chemistry program. I'm not going to talk about any science, but I thought Professor C.P. Rao told me that it's all about addressing the students and sort of giving them some motivation. I thought I'll talk to them about what makes basically MSc chemistry and IIT setup different from the university setup, and sort of leave them with some kind of glimpses into the kinds of challenges that the humankind today is faced with, and how chemistry can rescue us and the challenges ahead, and how the younger generation can basically sort of own up the challenges and to rise against with time to come. Well, personally, I would have liked to come, and in fact, the director said this, but Corona has sort of precluded any such possibility. But the other way to look at it is that the online platform allows everybody to come together. In fact, I've been listening to the talks, and what a fantastic startup it was from Professor Balram. He laid the fantastic foundation for what to come, and how chemistry is so relevant to our life. I was just wondering, I come from a Bangalore University. I did my master's in Bangalore University. I come from a university structure, but then started teaching masters in IIT. And I always pondered how basically education in IIT is different when compared to that from universities. I think this is for the benefit of the students. Right? When you go to the university, be it nowadays, you have mushrooming of a lot of PG colleges, PG centers, and somebody teaches, somebody sets the question paper, somebody evaluates, and the university basically declares the results. On the other hand, in fact, when you talk about the curriculum and the syllabus is not updated regularly, right? On the other hand, in IIT system is a semester based, of course. The teachers that teach you basically grade you. There is a personal contact all the time. There's a close interaction. You grow up as a family. In fact, when I joined IIT Kanpur 1998, and Professor Pippularao told me that the number of students that are admitted is about 15. In fact, even in 1998, 99, Professor VC is there, Professor Satyamurthy, and several colleagues are there. The number of students was about 15. We pretty much knew every student who was graduating those days. The beauty of having basically smaller strength is that the teachers know you well, and you know the teachers very well, and there is a strong bonding that develops with time. And I was talking about the curriculum, I mean the syllabus. The syllabus is very not updated from time to time in universities, but on the other hand, the beauty with IIT systems is that you have basically the scientists carrying out the contemporary science, being engaged in frontline research, teaching you. As a result, what flows to you as students is basically updated, contemporary, I mean, absolutely today's information, which you otherwise don't get. I'm not condemning the universities. There are, of course, several universities where a very good science, a very good teaching happens, and there are a lot of people who carry out frontline research. But clusters I'm talking about in IITs, you have, the infrastructure, facilities, the kind of research that goes on is fabulous. And I told you that the teachers take a personal interest in you, not only completing, but then getting placed, and which is where the department takes pride, the institution takes pride about your placement, which otherwise doesn't happen in the university. There's a huge difference when you compare basically the education the university setup vis-a-vis the education in the IIT setup. I thought, I should tell the students how lucky they are to be part of the IIT system, and getting started with a new system where there are not large number of faculty, but minimum number who are passionate about teaching. And as the department grows, you grow, and the personal bonding that happens will, probably about for 10 or 15 years down the line, the students that join will not have the same benefit as you, the newcomers, have. Coming to chemistry, I think chemistry is a central science. I think Professor Balram said it's a science of matter. And maybe I recall what Linus Pauling said in the context of chemistry, who is he's a two-time Nobel laureate. And there's a popular quote. And according to him, those who don't know chemistry are missing great happiness in life. Absolutely true. The chemistry is such a charm. Also, someone else said, it's a window given to the humankind to glimpse into the materials world, right? If you are to basically if I have to explain what this glimpse into the materials world, I think suffice it to say, every one of you know what OLEDs are, organic light emitting diodes, right? We basically transited from cathode ray tube technology, black and white televisions, to all kinds of technologies. Now today you have a brilliantly viewable technology, organic light emitting diodes. It's a materials, right? It's a kind of a glimpse that God has blessed with the humankind. Talking of the challenges, I would like to pose you a question. What do you think are the great challenges faced by the humankind today? Right? If I am to take a class, probably I could pause and then pick out a few students and try to elicit their responses, but I'll not dare do that now. It's not possible. But let me tell you what are the great challenges that the humankind is faced with. Of course, we all know climate change. The temperatures are shooting up, floods everywhere, irregularity in terms of the seasons. We attribute that to global warming. Energy is a crisis. We have fixed deposits of fuels. Mother Earth cannot basically sustain this. We have to look at alternative energy sources. We are now looking at basically in a place like this, wind power, photovoltaics, solar energy is incessant energy and can be tapped, and which is how we have basically solar heating systems and everywhere. And we're looking at even the biodiesel as an alternative, photovoltaics, how we basically store the energy and then use it. Water, no matter what the technology, I'm sure Pradeep is going to talk about water. Everywhere, water everywhere, but still not a drop to drink. The saga goes on. Still, we need to have basically technologies to take care of a lot of population that is depleted, deprived of pure water. And the biggest concern, I think, in years to come is waste management. Right? Everywhere we use, just basically to pack my food, I have plenty of polythene and aluminum foils. Worry about basically the gadgets that every one of us uses. We produce, and the production happens by drawing all the resources from the Mother Earth, from fixed locations, and they get dispersed everywhere in the earth. What happens eventually? Can we sustain this? Sustainability is a big thing. We use and throw, but what happens to the material that is thrown? Can we recover it back? If we don't, then I think we'll be running out of basically the stocks very fast. Waste management is a huge thing. It's a big challenge in the years to come. Of course, I thought I'll talk about 5 challenges: climate change, energy, water, waste management, I said, is a huge thing, and infectious diseases that we are all basically fraught with today. Coronavirus, who doesn't know? We just recently had, a few years back, we had Nipah, Ebola, influenza viruses, all kinds of diseases from time to time. Challenges are vast, but who comes to the rescue of the challenges that the humankind is faced with? None other than the chemists. It's the chemists who have to basically salvage the humankind. And it is from that point of view, I say, chemistry is really evergreen. I think you should consider yourself really fortunate to have taken up this exciting and exotic branch of science, science of matter, right? Solutions should come from chemists, absolutely. But then what do chemists do? We have to understand how basically the reactions occur. How basically molecules aggregate, which is where the mechanistic chemistry, we go to what is called as supramolecular chemistry as to how molecules come together. When you talk about basically a property of a material, it's a basically association of the molecules that lends a certain property to the solid matter, the bulk matter, right? And if that is the case, we have to worry about making such molecules in a manner that you can basically control the properties from molecules to materials. So you have to understand basically the reactivity patterns, association patterns, and then only you can correlate basically the property. And which is exactly what I work on. I worry about basically reactivity, how molecules undergo reactions with light, organic photochemistry, and how molecules self-associate as what we term as supramolecular chemistry. And if you know how to assemble the molecules, you can worry about controlling the properties by a specific organization, because the bulk material properties essentially depend on how the molecules are associated, right? And at the end, you have to make the molecules, and which is what brings you down to the organic synthesis. So I work on organic synthesis, organic photochemistry, and supramolecular chemistry. I look forward to coming over there one day and then share the excitements of my chemistry with them. And while being at that, and as I said, I would like to wish a new department to grow to a newer heights, and a position itself like the IIT Kanpur that is renowned for. And of course, now we have IIT Bombay also in the league, where Professor C.P. Rao comes from, right? Position itself as an excellent department to attract brilliant minds for the master's program in chemistry in the country. All the very best. Thank you very much.
Thank you, Mr. Murthy.
Thank you, Professor. Thank you, Professor Murthy, for joining us in the middle of his journey and passing the encouragement to the new students. Thank you once again.
Thank you.
Our next speaker is Padma Shri Professor T. Pradeep. Professor Pradeep is a Deepak Parekh Institute Chair Professor at IIT Madras. He has received many notable achievements, which includes Young Scientist Award from Chemical Research Society of India, Sharna Jayanti Fellowship by Department of Science and Technology, J.C. Bose National Fellowship by Department of Science and Technology, Lifetime Achievement Research Award from IIT Madras, the World Academy of Science Prize in Chemistry, Padma Shri from Indian government, Silver Medal from Chemical Research Society of India, National Research Award in Nanoscience and Technology by the Department of Science and Technology, and many others. He is the Fellow of Indian Academy of Sciences, the Indian National Academy of Engineering, Royal Society of Chemistry, the Indian National Science Academy, National Academy of Sciences, American Association for the Advancement of Science, the World Academy of Sciences. He has done significant work in the area of molecular and nanoscale materials, nanoscience, nanotechnology, water purifications, and several other allied topics. I request Professor Pradeep to share his experience with us. Professor Pradeep. Sir, please unmute your microphone.
Is my
Professor Pradeep, yeah.
Can you see my screen?
Yes.
Well, thank you, Professor Pularao. Thank you, Satya, for this invitation. Welcome to the young minds. Welcome to the world of chemistry. Welcome to the world of molecules. This 10 minutes of this 10 minutes dose of wisdom given by all of you was so concentrated that it will take a lifetime to digest all of that. I thought I will share with you the excitement in our laboratory on this theme, new molecules. Jayan Murthy talked about water. This is something that I work on, but I will not be talking about it today. The world is all full of molecules. And one way to see molecules is is by mass spectrometry. And this is a tool that, that was developed over 100 years ago. And the first textbook was in 1913. And today, you can make molecules like these, as you can see on the screen. And there are techniques of mass spectrometry with which you can observe the composition of this. So here is a mass, and this mass is so precise, 7390.5718 here. And this mass range is so vast. So here, this mass range is only up to 10,000, but today's mass spectrometers, the most advanced mass spectrometers, the new techniques in mass spectrometry can get you masses of something like 10 megadaltons. 10 megadaltons. That means you can measure the mass spectra of most viruses. And people have also, in fact, there are examples of measuring whole bacteria. You can measure this with atomic precision. So this particular molecule that we have synthesized in the laboratory is gold-25, a ligand 18, 1 minus charge state. This mass spectrometry, the method of mass spectrometry is called electrospray-ionization mass spectrometry, which won 1/4 of a Nobel Prize long ago. Why am I talking about this? Today we can measure masses of this kind with so much of precision, as I told you, you can get isotopic composition. So in a synthesis, if you get this kind of a structure, this kind of a material, for that is uniform, you can crystallize it. And when you have this, you can get structures. You know how these atoms are arranged in this. Today, there are several such molecules. For simplicity, let me call it gold-25, silver-25, silver-29, and many others. There are over 300 such molecules. Obviously, when you have something like this, chemists ask wonderful questions. Is this piece of matter a metal? If it is possible, can you increase the size and see where metallicity comes up? If this is made of not just gold or silver, if this is, let us say, made of some nickel, you can ask this question, is that ferromagnetic? Will ferromagnetism, at what size ferromagnetism appear? Very many questions. And these questions are not new. So these questions have been, when it comes to metallicity, this question something like 150 years old. Many great chemists and physicists ask these questions. But today we have mechanisms or methods to make those. So we ask one such question. You have this piece of matter, you have another piece of matter. For simplicity, as I said, gold-25, another molecule, gold-44, silver-44. We ask this question, will they react? Just as molecules react? Will these nanoparticles react? And we found that they indeed react. And to show you an example, here is 125, this is another 25. Can I have a reaction like this? And we showed that here is the mass spectrum of this molecule, which I call 025 to indicate that there is no silver in it. It is only purely gold-25. Here it is purely silver-25 and no gold in it. These are two pure species. You mix these two together and they start reacting. You see one atom of gold goes away and a silver comes in and it becomes totally 25 atoms, but it is 124, 1 silver and 24 gold. So here correspondingly, 24 silver and 1 gold. Atoms do exchange and then they keep the same nuclearity, but there are many other peaks here. There are many other exchanges that happen. How do they happen? they come together and form a dimer. AU25 and AG25, they dimerize and they form this kind of an entity. Is there thermodynamics in this? Is there kinetics in this? Yes, of course. All of these are there. Now we thought, can there be something even more exciting? We saw rapid isotopic exchange. So here is an example. Take silver 25, then we can make 25 isotopically pure. Silver has two isotopes, 107 and 109. We can make silver 25 with 107 alone. We can make silver 25 with 109 alone, just like making H2O and D2O. We can get a mass spectrum. Here, the mass spectrum corresponds, or peak corresponds to 5142. This peak corresponds to 5192. The difference between this is 25 atoms. The difference between one silver is 2 atomic mass units. So 25 is 50 atomic mass units, 5142 and 5192. You see something exciting happening. 5142 and 5192 are two separate molecules. You can make them in a bottle, but you mix them together, H2O and D2O. When you mix them together, what happens? Atoms, when you mix them together, they exchange. You get HBO. Similarly, 25 of these, you make double the number of this species, which is isotopically mixed. How fast do they do this? Well, first 15 seconds, you barely see these species. 20 seconds, almost gone. 25 seconds, it is finished. 30 seconds, it is completely over. Atom exchange is so rapid in materials. Of course, you have kinetics and associated things of this kind. What does this tell you? Today's mass spectrometer, I told you, can go to megadalton. That means 5,000, 10,000 atoms of gold nanoparticles can be seen. You can make them. And you can make them atomically pure with specific composition. When you start mixing them, when you start reacting them, you can get very many exciting possibilities. But the periodic table is so vast. So many different clusters and nanoparticles are possible. So many diverse kinds of properties are possible. All of these can be examined with atomic precision. What it means is that molecules of this kind are everywhere. With that vision, if you look around, everything that is around you is a molecule, is atomically precise. Atomically precise materials can be characterized, and that characterization or that study will tell you that everything around you is chemistry. Thank you very much, and I wish you a fantastic journey into chemistry.
Yeah. Thank you, Professor Pradeep, for sharing the insightful words and also sharing with us the excitements of the nano world. So, as our next speaker, we are very happy to have Professor G.K. Lahiri. He is a professor at the Department of Chemistry, IIT Bombay. He is also the Institute Chair Professor at IIT Bombay. Professor Lahiri has received many awards and distinction. To name a few: J.C. Bose Fellowship from DST, CRSI Silver Medal, Reverend Father L.M. Edanapalli Memorial Award by Indian Chemical Society, Professor S.C. Bhattacharya Award for Excellence in Research by IIT Bombay, Royal Society Award for International Authors, B.M. Birla Awards in Chemistry, and many others. He is the Fellow of the Indian National Science Academy, National Academy of Sciences, Indian Academy of Sciences, Maharashtra Academy of Sciences. His major research interests are in the field of metal ligand frameworks and catalysis. I request Professor Lahiri to share his experiences about the excitements and challenges he found in his research domain. Professor Lahiri.
Am I audible, CPR?
Yes, yes, yes.
Okay. Let me begin by expressing my appreciation to Professor C.P. Rao for taking this very nice and rather very unique approach to address the newcoming MSc students. I would also like to thank Professor Satyanarayan, Director IIT Tirupati, for being introducing this MSc program in the chemistry department, IIT Tirupati. And I also would like to congratulate all the students who have joined through this JAM program in the Department of Chemistry, IIT Tirupati. Now, I thought to talk in a general sense instead of taking any particular issue in the slide form. I hope it would be fine. So now, if we to address the students, they also need to know that exam what they have qualified to come into the IIT system. Today's context, we call it the JAM, and it has a very nice history and genesis also. I think way back, if I'm not too wrong, around 2000, Professor Satyamurthy from IIT Kanpur, he took this initiative to start this national single exam for this MSc admission in the IIT system. And that time it used to call GA, I think JAT, Joint Admission Test or something like that. And in the initial year, only 3 IITs joined in this program. That was IIT Kanpur, IIT Bombay, and IIT Madras. And then, if I'm not wrong, next year IIT Delhi joined. And subsequently, I think 2003 onwards, around that time, the name has got changed from JAT to JAM, and that means Joint Admission in MSc program. And then slowly all IIT come under the same umbrella of JAM. Now, if you see the JAM exam, it's a big national test, single platform test, and by which we select only a few students for each IIT, and they come from all over the country, from various colleges after completion of their BSc program. So basically, we get very high quality BSc students, and they join in our program. And I think for IIT system, the MSc program in any science department, particularly in chemistry, which is very important and essential, because it would be their flag bearer brand item in the department. Now, if you look at the IIT system, it is essentially engineering institutions. Science departments are generally, if I understand correctly, they are the serving departments to the engineers and all sort of things in a general sense. Okay, but it is also true that the science departments contribute to a large extent for the growth of the IIT system, particularly in the research domain. Okay, now if we do not have the brand MSc set up in the department, that means the teachers, the faculty members would only be involved in teaching the engineering first year UG program. And besides the PhD programs and their other administrative activities. But this first year teaching program is very important because we get chance and opportunity to teach the very bright students who come through the JAM exam, etc., etc. But because of the time constraints and other parameters, we do not get much opportunity to go beyond the surface of the subject. We only restrict ourselves in certain topics which attracts, normally engineers, they don't like chemistry much, but still, it's okay. But when you come back to the MSc program, where the faculty members essentially find the enormous opportunity to spread their, scientific wings, and they can move into the advanced topics, advanced teaching programs, research program, and all sort of things. And that is very essential from the faculty point of view. Now, if I look at from the students' point of view, well, they must remember that they are the only few out of many who try to come to the IIT system, that they get the opportunity to come to the IIT system. It's a very unique system where teaching pattern is very different than what it is being practiced at the university levels and other places. and they're in IIT system they get very high quality teachers. They try to cover many things, and if we see the growth of this MSc program in the IIT system, particularly my experience at IIT Bombay, we see that we have integrated program where the students join after the higher secondary level through the JEE. They are very bright, and they join the 2-year MSc program at the earlier is to 4th year level, but now we have a 4-year BSc program. Now I would like to highlight this point to the students who have joined this program, that we have integrated program nowadays. It is called 4-year BS and the 2 years program. And that integrated students, they are very bright. But when they reach to the 3rd year or 4th year, I think their enthusiasm, declines exponentially. And as a matter of fact, in spite of their bright nature, they cannot grow the way chemistry wants them to grow. And many of them move into, management, these, that, and all sort of, but of course they are very established. But if we look at the 2-year students, our experience is they're always very enthusiastic. They want to understand the subject. They want to interact with the colleagues. They want to grow in a better and better way. And as a matter of fact, over the last 3 decades, what I have been observing, the most of our students, they normally go either abroad or in the good institutions in India. They do their PhD, followed by postdocs, and they are being highly established in different academic institutions, both in abroad and India, as well as in industries. Now, if we look at the Indian scenario, I see our students, and more particularly the 2-year MSc students, they are in most of the IIT systems as a faculty members, IISERs, NISERs, and national institutions. That's a matter of great pride. And I'm sure that those who have joined today in this MSc program, they would have also the similar kind of future, but provided they can continue with their enthusiasm till the end of their academic pathway. So with this brief introduction, I would like to tell them that enjoy your association with the IIT system, not only just by academic means, but also non-academic means. IIT offers many other things which one could enjoy to a large extent. And I personally had visited IIT Tirupati as a wonderful campus. So, and the campus is, of course, new campus is coming up, and you would enjoy the IIT, your stay in IIT academically and otherwise. And one point I would like to also address over here, what I find which is unique in nature as far as our academic program is concerned, that is your project component. And I'm happy to see the slides what Professor Rao had shown in the beginning, that there is a 1-year project component. And this 1-year project component at IIT Bombay, we see the great success in it because of the fact of the students, each and every students, 2-year MSc or integrated MSc, whatever it might be, they get the right exposure, hands-on experience, how to do research work. And what we have noticed, that many students, they spend their 1-year project time very seriously, and at the end of the day, they could also publish good quality papers out of their contributions through this MSc project program. And Professor Rao has rightfully introduced that component for 1 year. So I must appreciate and praise this effort by Professor Rao. And the last point I would like to mention to all the students, remember that today's context, as far as teaching is concerned, we talk about physical, inorganic, organic, all sort of things. But the research is completely a different story, where there is no boundary, and where both inorganic, organic, physical, they come together to do something great, something useful for the society, either from the growth of the knowledge point of view or from practical utility point of view. And if we, being an inorganic chemist, I would like to say that inorganic, it has of no character. Character in the sense, unlike physical and organic, they are very fond of their own branch. But inorganic, we sometimes don't like to say I'm an inorganic chemist. I prefer to say I'm organometallic chemist, material chemist, bioinorganic chemist, and so on and so forth, which is good in one sense. That means it can spread the wings the way it wishes to spread it. So I would like to, convey to the students, remain enthusiastic, study properly, and particularly take your project component very seriously so that you can enter into the research domain rather quickly, and wish you all the best in your future endeavor. Thank you very much.
Thank you, Professor Lahiri. Thank you for sharing your valuable experiences and reminding us the importance of the one-year project component and where the interdisciplinary nature of the chemistry comes in a bigger picture. So I hope the students will get the essence of your message and they will continue to do good work in their future life. Thank you, Professor Lahiri, once again. So our next speaker is Professor Vijay Mohan Pillai. He is the former director of CSIR Sikri and director in charge of CSIR NCL Pune, presently professor at IIT Tirupati. Professor Pillai has received many notable achievements, which includes Chemical Research Society of India Bronze Medal, Scientist of the Year Award by NCL Research Foundation, Material Research Society of India Medal, National Prize for Research on Energy Materials and Devices by JNCSR, MRSI, ICSC Superconductivity and Material Science Annual Prize, Outstanding Professor of the Academy in the Faculty of Chemical Science at the Academy of Scientific and Innovative Research, and many others. He is the affiliate member of the IUPAC, Fellow of Indian National Science Academy, Indian Academy of Sciences, Maharashtra Academy of Sciences, and Honorary Fellow of the Electrochemical Society of India. His research interests are batteries, fuel cells, bioelectrochemistry, electrochemical sensors, and other allied topics. I request Professor Pillai to enrich us with his experiences and say a few words to our new students.
Good morning. At the outset, I would like to thank Professor Satyanarayana and Professor C.P. Rao for making me a part of this program to launch the master's program at IIT Tirupati. I also welcome all the 14 students. And we know how difficult to get into this 14 number. So let me first congratulate all of you. It's not very easy, but you are all the people who are going to make chemistry more exciting in the maybe next few years. Please remember that chemistry, like all of us, move on 2 feet. One is called curiosity and the other one is called utility. Both aspects are almost blended. In certain areas, you will see curiosity is predominant. For example, Professor V. Chandrasekhar talked about batteries, energy, environment. Professor Jayan Murthy also talked about most pressing challenges we face, humanity faces, including the pandemic. So if you list all these challenges, the whole humanity faces, whether it is affordable water, energy storage, recycling, or even if you consider about the wars. So all major problems, chemistry can come with solutions. What is interesting is that when you come, don't approach, because just like Professor Lahiri mentioned about chemistry, there is no boundary at all. We can say the boundary is molecular boundary. So last 10 years, maybe even 20 years of evolution of chemistry as a whole, if you look at it, so many things have happened. And chemistry's boundaries are always dynamic. There is no other branch where you will see chemistry is contributing so much more. Take developments such as electrical engineering or electronics. We talk so much about wearable electronics. When we talk about millions of sensors integrated on a small conducting polymer-based clothing, the power source is also integrated, sensors are embedded. Chemistry is extremely important. That is why we say chemistry is an enabling science. So chemistry had a great past. Chemistry is an enabling, actually present, and there is a future, highly promising future, more exciting future. So I am glad that all of you would be a part of this exciting future. I thank IIT Tirupati for launching this program. Please remember that you have had advice from many of our elders, including Professor Satyamurthy, Professor Balram. They have all given you the distilled wisdom by last 30 years of teaching. Where chemistry is heading. Chemistry's movement can be tracked, of course, in several directions, multi-path, but one or two directions emerge very clearly. One of them is chemistry-biology interface. Whether it is designing a new drug, and please remember, any drug if you want to design, there will be a set of computational engineers designing this drug. So quantum chemistry plays a critical role in designing new drugs. Wherever there is a 3D printing of an organ, the mechanical engineers will come and do the design of the 3D printing. But the inks are made by chemists. Whether you want a silicon predominantly, hydrophobic ink, hydrophilic ink, all that part comes from chemistry. That's the reason why I talked about. It is impossible to separate chemistry from any other branch. Metallurgy, material science. You have heard enough about material science. So I would say that chemistry's dynamism is more discernible in two interfaces. One is chemistry-biology interface. A cell could even be considered as a bag of chemicals, lot of chemicals, whether it is ribosome, mitochondria. Mitochondria is dead bacteria. So that means you also have emerging areas and frontiers which are continuously changing. This is the reason why chemistry is more exciting. Chemistry also connects you to mundane things. What happens in our daily life? Chemistry of oceans, chemistry of atmospheres. I'm sure all of you know, we have sent a spaceship to Mars. NASA has sent it just last month. It is going to reach Mars in somewhere around February 2021. The moment it goes to Mars, there's a helicopter called Perseverance. The crater where it is going to land is already identified. Why is it interesting? Because for chemists, there are many critical issues there. Number one is that the moment this rover called Perseverance lands there, we need to convert CO2 to oxygen. There is no oxygen. Mars has so much of CO2. So future, we think about colony in Mars. How do we generate oxygen? There is an electrochemical device in this Perseverance. The electrochemical device has one critical job: convert CO2 into oxygen. How do you convert CO2 into oxygen? Electrochemistry comes to help you. Just like Professor Chandrasekhar talked about lithium batteries, flexible, bendable, next generation power sources. So please remember, energy generation, energy storage, and energy conversion, they are all done tangibly by chemistry. Materials is another area. You have heard many of my predecessors spoke about materials. These days we have got wonderful materials, almost magical materials. Material which knows what is around, what is happening in the environment. Materials which can think, materials which can act, intelligent materials. So you will see that all these cases, chemistry plays a critical role. Don't worry, organic, inorganic, bioinorganic, they're all not important at all. All of chemistry means manipulate compositions, atom by atom, molecule by molecule, look at whether the properties can be changed. And last 20 years, we have got so much of understanding in chemistry because of its multidisciplinary strength. Even artificial intelligence comes and contributes to chemistry. The first book written by machine intelligence is on lithium-ion batteries. Please remember, electric vehicles are very important. How did we get so much importance for electric vehicle? Because of chemistry. Plenty of material. Lithium, cobalt, nickel. Where nickel goes, where cobalt goes. How do we manipulate the defect engineering? All that can be answered thread by atom by atom, molecule by molecule. That is why chemical transformations is the basis of most of these phenomena, including life. This is the reason why I mentioned that biology, chemistry interface, chemistry, and materials interface. These are the two cases. Even if you have a spaceship going to touch sun, how hard materials can be defined, how hard materials can be designed, again in the laboratory. So I am glad that all of you have taken that you are going to study chemistry, learn chemistry. Your enthusiasm and your excitement will make sure that chemistry advances at a faster rate. I would like to compliment IIT Tirupati, and we are always there. IISER is always your neighbor, and we have got fantastic team of chemistry. We have a culinary chemistry. Chemistry, I'm sure Professor Ganesh will talk about it. If you want vada and dosa, what is the difference? Both have almost 90% carbohydrate. Why vada looks with a golden color, idli looks white. How do you understand what happens for this carbohydrate when they react with a certain amino acids? Why the chocolate brownie is so tasteful? Or if you fry chicken, what happens? Maillard reaction. So please remember, chemistry is always an exciting field, also for food. So we have a food chemistry, we have a forensic chemistry. If somebody kills or murders, throw a knife into a pond. After 1 year and after 1 day, chemistry will help you to find out. Forensic chemistry. So there are plenty of unopened areas where the knowledge of chemistry can be extremely useful for human welfare and also for society. Energy, environment, recycling. That's the reason why I'm telling that you are lucky. You be proud that you are going to be a chemist. Like Professor Rao, Professor Sina Rao, a typical chemist from India who is most well known, says that, look, I am a chemist. He does a lot of physics. He publishes in fantastic physical journals, including Physical Review Letters. But primary interest is chemistry. There are several physicists who have got much stronger affiliation with chemistry. Professor Oppenheimer has done so much, including nuclear bombs, but his first love was chemistry. Feynman's affection for chemistry was mentioned by Professor Balram. I'm sure that all of you will be proud that you have taken a noble career, which is going to be of extremely important use for humanity's welfare. And this landscape will change. It doesn't matter whether we go to Mars or Moon, chemistry will always be alive and kicking. So with this, I would like to once again thank all of you for your patience and my best wishes for you. We are there, we are the neighbor. Anytime, any help with respect to any aspect of chemistry, theoretical, experimental, electrochemistry, or even projects, don't worry. We have a credit sharing system, and we are also going to do a Center for Energy combinedly, and also an instrumentation center. I'm sure Professor Ganesh would give you more details. With this, my best wishes to all the 14 champions who are going to do next generation chemistry. Thank you all.
Thank you, Professor Pillai, for your blessings. And I'm sure that all the students know if they lack any excitement, whom to talk. Thank you for showing such an exciting speech to our new students. Thank you, Professor Pillai, once again. So our next speaker is Professor G. Mukesh from IIT Bangalore. He is a professor in the Department of Inorganic Physical Chemistry, IIT Bangalore. Professor Mukesh has received many awards, which includes J.C. Bose National Fellowship by DST Government of India, Infosys Prize in Physical Science by Infosys Science Foundation, CRSI Silver Medal, Santi Sharu Bhatnagar Award by CSIR, CRSI Bronze Medal, Swarno Jayanti Fellowship, IUPAC Young Chemist Award, and many others. He has been the Vice President of the CRSI and also the President of the Asian Chemical Editorial Society. He is a Fellow of Indian National Science Academy, Fellow of National Academy of Sciences, Fellow of Academy of Sciences, Royal Society of Chemistry. He has contributed significantly in the area of chemical biology, bioinorganic, and medicinal chemistry. I request Professor Mukesh to say a few words to our newly joined students. Professor Mukesh.
Okay, we will go to the next. And okay. Yeah. Let's. Yeah. Yeah. Okay. Yeah, seems Professor Mukesh has a problem with the connection. He's trying.
Okay. Okay, we'll wait.
And if he's unable to attach, then we can probably go to the next speaker.
Fine. So, shall we wait for him a couple of minutes?
Yeah, just wait for a minute or something. He's trying.
Sure, sir.
Yeah. Is Saurav Paul is back?
I think Professor Pal is there.
Paul is there? Yeah, okay. So then we can.
Yeah, so. So let us wait for a few more seconds for Professor Mukesh to join.
Yeah. Let's see whether the call is ready.
Professor Pal is also not there.
Response there? Not
No.
there?
He was there.
Sit there. Hello. Mukesh? Hello. Okay.
All of you can have your coffee. This is a good coffee break.
Okay.
Yeah.
Okay.
Maybe it's a good idea to
Thank you.
take.
Okay. Okay. Thank you. Thank you.
Yeah, I think Umapati is having coffee.
No. No permission is necessary.
Yeah, he's still having problem, Professor Mukesh.
What about Saurav?
Can we go with next? Is Professor Paul is there?
No, Professor Pal is also not
Not there.
here.
Okay.
He was there.
Yeah.
No, it is the problem is not from our end.
Gauri, can you please contact Mr. Paul?
Yeah, he is speaking with Professor Pal.
Ah, Mukesh.
Seems he is also having some trouble to join
Hello.
the meeting.
Connection. Okay.
No, there is no waiting room at all.
No, they can join anytime.
Yeah. I cannot skip to speaker and call Professor Ganesh because he will give the concluding remarks. That would not be wise to call Professor Ganesh now.
Vashish, I think it should be fine. Professor Ganesh can view his comments so that we don't time. It's not necessarily concluding.
That's okay.
Please go ahead. Please, I
Okay.
think Professor Ganesh to go ahead.
Is Professor Ganesh is there?
Professor Ganesh is there, I guess. Hello, Professor
So
Ganesh.
I think, 1 second, I think Mukesh will speak on the phone. Is it okay with you guys?
Sure. That is
Yeah, no problem. No problem. Yeah.
Put it in the speaker mode.
Yeah. How
So
would
can you speak, Mukesh? Yeah, now you speak. Yeah, can you speak? Oh, you call CP Rao. That's probably better. Yeah, call CP Rao. Yeah, okay.
Call Gauri Prasannan. Call Gauri.
Oh, he disconnected.
Yeah.
So we are calling him, sir.
Yeah, you call him.
Huh? HOD chemistry. It's given.
Balram, you are muted. We can't hear you.
You've changed your background.
Yeah, so what to do?
I always knew you were very bad at stereochemistry.
Yeah, exactly. I mean, if you want to be good at something, you can't be good at chemistry. That's why you went to biology, isn't it? Good to see you, Balram. The same spirits.
Okay. Okay.
What is that in the background, Uma?
Oh, it's our institute, actually. It's a hostel, student hostels.
Is the grass?
What you're seeing is it's a student hostels. Much behind is the other academic blocks.
Professor Pularao, I think we should not be wasting everyone's time. Let Professor Ganesh go ahead.
We got Professor Mukesh over telephone. So yeah, so he will be speaking over telephone.
Yeah.
Professor Mukesh, please go ahead.
Can I start? Yeah.
Sure, sir.
Good morning to all of you. I'm sorry for this technical problems. our Wi-Fi in the institute was working fine till now, but suddenly it started giving problem. It disconnected. So anyway, I would like to thank Professor Satyanarayana and Professor C.P. Rao for inviting me to speak in this meeting. And I looked at the title of the presentation, Bird's Eye View at the Excitements and the Challenges in Chemistry. We listened to excellent talks by very experienced teachers and researchers. I will only try to share some of my thoughts on excitements and challenges. I will not be making any PowerPoint presentation, so I will just speak over the phone. Science and particularly chemistry is becoming more interdisciplinary. Understanding life at a chemical or molecular level continue to help in improving human health. I think we should also keep in mind that understanding chemistry alone is not sufficient, and linking to other disciplines in a proper way is crucial to address bigger problems. You will agree with me that making new molecules is a fascinating area. Chemical synthesis, that is the making of new molecules, is at the heart of chemistry. The synthesis of new molecules in a laboratory, as a synthetic chemists know, is not very difficult. But making molecules with a desired function is challenging. For example, rational design and synthesis of small molecules, peptides, and proteins that can regulate biological functions is extremely important to understand and treat diseases like cancer, diabetes, cardiovascular diseases, and neurodegenerative diseases. We have been studying the chemistry of biological system for years, but can we use this knowledge to design and synthesize molecules that can regulate the cellular function or an organ's function? The year 2011 was celebrated as an International Year of Chemistry with the theme, Chemistry, Our Life, Our Future. And last year, 2019, was celebrated as the International Year of Periodic Table. And the introductory talk, Professor Balram mentioned about the periodic table of chemical elements, which is one of the most significant achievements in science, capturing the essence not only of chemistry, but also of physics and biology. As you all know, chemistry is taking new directions. The chemistry of materials, for example, energy-related materials, chemistry of the environment, atmosphere, and the chemistry of life processes. If we look at chemistry, these three areas becoming a department triad in many universities. And when it is combined with the triad of responsibilities, that is teaching, research, and service, chemistry can contribute remarkably to the well-being of humankind. The IIPT, the International Year of Periodic Table events last year, celebrated the 150th anniversary of discovery of periodic system by Mendeleev. Have you ever wondered why only approximately 28 elements out of 118 elements are essential for biological function? When calcium is present in kilogram quantities in human body, why the nature chose only 4 grams of iron and just 1 milligram of cobalt. It is interesting to know how the human body uses 1 milligram of cobalt as part of vitamin B12 to mediate chemical reactions that support life. We know that rusting takes place when we keep an iron rod in contact with oxygen and water. Our body has 4 grams of iron, plenty of oxygen and water. Why we do not talk about rusting of iron in human body? If the proteins cannot use the right coordination chemistry to control the free iron, rusting can take place in the human body. Neurodegenerative diseases such as Alzheimer's disease are associated with such dysregulation of metal ions in human body. We all know that zinc, cadmium and mercury belong to the same group of the periodic table, group 12 elements. We also know that this set of elements in a group should have similar chemical properties. While zinc is essential for the catalytic function of more than 300 enzymes, cadmium and mercury are toxic. Why? I hope you all familiar with the Minamoto disease. Mercury toxicity played a major role. What chemical properties make zinc unique? We all know about ATP. ATP, the main source of energy in the cell. ATP must bind to a magnesium ion in order to be biologically active. In contrast, beryllium, just one element above in the periodic table, is toxic to human. In fact, beryllium is one of the most toxic elements we know. Why? So we need to look at the challenges, how the chemistry is being developed, linking the fundamental chemistry that we teach in classes to the real-time applications, and developing expertise in newly emerging areas are the challenges. We study about periodic trends, atomic size, ionization energy, electronegativity, etc. We hear from students that these topics are boring and how they are relevant these days. But one should understand why a change in the size of a single atom can save our life. If iron does not change its size from 78 picometer to 61 picometer upon oxygen binding in hemoglobin, no oxygen transport can take place in the human body. 2 weeks in mountain can change your blood for months. What is the molecular basis for this? You may be aware that the 2019 Nobel Prize in Physiology or Medicine was awarded to 3 scientists for their discoveries of how cells sense and adapt to oxygen availability. I'm sure understanding chemistry played major roles in their discoveries. As students, questions. You should learn to adapt to the changes and deal with the changes. It's important to realize it early in the career, and resisting changes can only make it harder. No one enjoys change or uncertainty, but embracing change enables you to thrive. I take this opportunity to wish you all a successful career. Thank you very much.
Thank you, sir. Thank you, Professor Mukesh, for sharing your excitements and valuable advices to our newly joined students. Our next speaker is Professor Saurabh Pal. He is the present director of IISER Kolkata. Professor Pal is a former Institute Chair Professor of IIT Bombay, former director of CSIR NCL Pune, and also he has served as the director in charge CSIR Central Salt and Marine Chemicals Research Institute, Bhavnagar. He has received many awards. To name a few: Shastra C.N.R. Rao Award in Chemistry and Material Science from CSIR, J.C. Bose National Fellowship from Department of Science and Technology, Shanti Sharoop Bhatnagar Award from CSIR, Chemical Research Society of India Medal, CSIR Young Scientist Award in Chemical Sciences, and many others. He is the former president of Chemical Research Society of India. He is also the former executive council member from Federation of Asian Chemical Society. Professor Pal is a fellow of Indian National Science Academy, National Academy of Science and Indian Academy of Sciences. I request Professor Pal to share his experiences with our newly joined students. Professor Pal. Professor Pal?
Is he connected?
Yeah, he was connected. Yes, he is there. Professor Pal, you have to unmute your mic.
Yeah, actually, I was trying to join through my laptop.
Yes, yes. Now we can hear.
We could hear you.
Somehow I'm not able to join. I will make one last attempt. I'm joining through mobile actually. So that's a problem. But let me just make one more attempt. But at this point, let me first thank all of you and Professor Pullarao in particular for inviting me to this session. If I'm not able to join, I still have my presentation on my laptop, so I can still talk without presentation. I think it's actually I was not prepared to present because Professor Pullarao said it's just an inspirational talk. So let me say that I think it's a very good idea that IIT Tirupati has started the 2-year MSc program. That's the very first thing. It is a very timely start because chemistry is very important. And I think being in ISAR, being at IIT Bombay, being of course at NCL, there is no doubt that I have realized over the years that chemistry is very, very important. As all of you know, of course, and I think I'm very happy to hear in the inauguration, I must tell to the students particularly that the healthy cooperation that IIT Tirupati and ISAR Tirupati have built up in not only sharing resources, but also sharing manpower. And I think that's a very, very good thing. The courses, and I'm very happy that there are many centers, joint centers which are being planned. In fact, I'm also very happy, I think Professor Ganesh and Professor Satyanarayan will remember when I visited IIT Tirupati and ISAR Tirupati, I had muted the idea of a center for chemical physics, atomic molecular physics. Basically, it's a chemical physics. And I've recently seen that that has already come out. I don't know exactly what stage it is, but I saw an announcement that it is coming up, which is a very nice thing. So I must tell the students, it's not very easy or not very common that the two educational institutions in India have collaborated like this. You may be surprised to know, but it has not been very easy. So I think I bless IIT Tirupati and ISAR Tirupati for starting this. At ISARS, of course, we are a research university, as all of you know. We do research and innovation. Of course, we want to do innovate. We want to do good things to the society. And the 7 ISARs are there. In fact, many of the ISAR directors already spoke. I saw Umapati, Jain Murthy, and Ken Ganesh, who is going to speak, I'm sure, next. I find that the ISARs together have already made a mark in the science landscape in this country. I think it's very important. So the ISAR Tirupati being very close to IIT Tirupati will also help. ISAR Tirupati will also get the benefit of IIT Tirupati because IITs have a different kind of focus in terms of innovation, in terms of entrepreneurship, in terms of translating chemistry to products. So I think this will be a great thing. So my very important message is that it is a great thing to celebrate that the IIT Tirupati has started this chemistry. So best wishes for a successful program. I must say that imparting fundamental knowledge is of course the key. Let's not forget, and I think Professor Pullarao, who has come from a good school, will acknowledge right away that one of the major challenges is to impart fundamental knowledge. Basic science, let's not forget about it. Yet, it is very important for the society that we must connect the basic science to the entrepreneurship. And I think the time has come, particularly in the context of IIT, I request that the chemistry be connected to entrepreneurship. Because if one science has a tremendous connection with not only industry, but with entrepreneurship, that is chemistry. Of course, chemistry is interdisciplinary. So chemistry cannot alone go. So just like in the COVID, we are now realizing that it's very important to understand biology. So the chemistry and biology must go together and provide challenges and solutions to the society. What we require is not just expertise. What we require is a solution. And the solution will not just come from chemistry. It will come from different branches. And this is where IIT is in a very good position. Because you have engineering. Many times I feel that even in ICERs, we require some kind of chemical engineering, process engineering, who can actually take chemistry processes from labs to the pilot plant and then to the industry, which some of the CSIR labs have been able to do because of the structure. But IIT should be able to do very well. Combine fundamental knowledge with industry, with entrepreneurs. Science education has a hierarchy. And I must say right away, this hierarchy, of course, science provides a basic expertise, let's not forget, and provides several opportunities. To the students, I must say, what are the opportunities first? Why should you do science? Not just chemistry. The opportunities are, of course, typical opportunities, who will become an academicians, get jobs in IITs, ICERs, NITs, universities, colleges, and so on. Private, government, I'm not distinguished at this stage, because many private universities are coming up very well, I must say that. Then you have opportunities for research in CSIR labs, IIC Bangalore, Tata Institute of Fundamental Research, Indian Association for the Cultivation of Science. I must say, many of these are also becoming institutions. They are also becoming teaching, like TIFR itself has a Homi Bhabha National Center, the Cultivation of Science, IIC Bangalore has an undergraduate program, CSIR labs. So everybody has understood that teaching is important. But what I'm saying, their focus has been on research. Then there are opportunities in mission-driven projects. And I must tell the students, where you work together, like atomic energy, ISRO, space, DRDO, defense. I think they provide great opportunities to work for the society. Then industry. Chemical industries will get better. And I can foresee that industries will take up challenging problems post-COVID. It's very, very important because there will be a lot of short supply. So industries have to gear up. So industry R&D is very important. And finally, of course, entrepreneurs. You also have to think that should we only look for jobs or should we create jobs? I think it is very important to create jobs. So entrepreneurship, which is called startup, and I'm not talking of jugaad. I'm talking of startups which are based on what is called deep innovation, high science innovation, and let's do that. Then, however, there are many other options. For example, you can take alternative science career, journalism, science for society, public outreach, to make science popular. Look at international collaboration, opportunities. So there are several things that the students will be able to do. But those who are interested in fundamental science, they must realize that the fundamental science cannot often be predicted. Many people think that it is curiosity driven. Not necessary. I think a great example is the synthesis of urea. It's an accidental synthesis. Great example is the discovery of Archimedes, which was driven by necessity, that the king hero told him that he must find whether the goldsmith is cheating or not. Otherwise, maybe he would have been killed. Who knows? So that was a necessity for Archimedes to discover. So it's very hard to predict what gives in fundamental science. Of course, we are obsessed by the fact that Isaac Newton saw an apple falling. We don't know the story. And he became curious and found the Newton's laws of motion. That's great. But there are many other ways one can do science. Dream. Don't forget Fred Kekulé, who dreamed the snake seizing its own tail. So the history of, and then discovered benzene. The history of science is extremely important. But whatever you do, it's important that I had a very nice quadrant, which is called the Bohr quadrant, Pasteur quadrant, Edison quadrant. Many of you know 4 quadrant is a high science, low application. Edison is high application, low science. But what we need to do is to pasture quadrant, which is called use-inspired basic research. So we need to have basic research with a very good understanding. And I think this is where India has to move. We had, of course, some examples of great fundamental scientists in general in science, Indian or Indian origin, like Sir C.V. Raman, S. Chandrasekhar, Hargobind Khurana, Venki Ramakrishnan. Although many of them did not work from India, I think we have to create more examples. I have to tell about chemistry versus physics versus biology. The hierarchy is very, very important to understand. When we grow up in school, we don't have any instinctive knowledge in chemistry. We have an instinctive knowledge in physics because we see the physics in daily life. The electricity, the light, the cricket ball falling, you can feel the physics. Biology is something that you see, but you don't see molecules. Except you know that if you mix A and B, something happens. Why it happens, how it happens, it's impossible to. So there is no instinctive knowledge in chemistry to start with, and chemistry looks very complex. That is the reason you'll find that in school level, a lot of students are interested in physics or biology. Very good students. So when you teach chemistry, and this is for the teachers, the 2-year MSc, that how do you teach chemistry? That itself is a big challenge. I've been always thinking, how do you teach chemistry? Chemistry has been taught traditionally by transfer of knowledge. That is the most popular process. Unfortunately, there's a considerable evidence that both the learners failing to make sense of the teaching and students developing alternative conceptions of the materials presented to them. Something is presented, they have some other idea. And that has been the big challenge of I'm telling certain things which are probably I have felt myself. Why is it so? Very strict, but there is a. So one of the hierarchy is that physics is built on mathematics. I don't know how you agree. You may not agree. To do physics, you must know mathematics. Then the second hierarchy is that chemistry is built on physics. The next level. Again, you may question that. These are very rough hierarchy. Biology is built on chemistry. Again, this is questionable. And psychology is built on biology. Again, questionable. There's a large part of psychology which does not depend on biology. Maths is, of course, clearly a tool, which is heavily used in physics and many other sciences. But there are very large parts of biology that do not make direct and indirect application of chemistry. Some of them make direct, some of them make indirect, but there is a large part of biology which is independent of chemistry. Similarly, physics also relies on chemistry. It's not that the chemistry comes from physics. But what I'm trying to say that this is a rough hierarchy that we have in our mind. And that is how this science has been built. At this point, I must pay homage to the first, whom I call the first chemist of India. I think many of you know his name. He died in 1940. I think he was the first Indian chemist. Many of you know today, of course, the hydroxychloroquine and many of the products Acharya had actually done. But what is more important is that he was the first one at that time who has started industry, Bengal Chemical, who started entrepreneurship. Today we are talking of that. So I must pay homage when you start chemistry of the Acharya P.C. Ray. He's one of the greatest chemists of all time. He of course got his degree from Edinburgh and so on and so forth. But from the Acharya's days to today, the chemistry has changed. How has the chemistry changed? It has gone from structure-driven to function-driven. Remember, chemistry used to be always structure. You synthesize something, go to NMR, go to HRMS, go to electron microscope. If it is materials, find out the structure, look for a function. But I think chemistry has changed. You have to look for a function first, and then from the function you have to look at the structure and analyze them. The barriers, hello, I hope I'm audible. Barriers of chemistry are already breaking down. There is nothing called organic, inorganic, and physical. We are driven by emerging trends of research. What are the emerging trends? Emerging trends are renewable energy, sustainable resources, energy efficient processes, environment-friendly process, affordable healthcare. And today we are talking about pharma. That's become very, very important. But remember, pharma is not just biology. It is biology and chemistry together. Cultivation of crops, farm cultivation, minimum land, maximum crops. Technologically enabled defense systems. It all requires chemistry as a challenge, and it requires a good amount of chemistry. And that is very important. But chemistry alone will not do. So it's important that to understand that there is a lot of interdisciplinary research that is required. COVID-19, of course, is going to pose a very different kind of problem. You need to protect environment, you need to protect climate, you have to bring in technological innovation. And of course, today, when you're starting MSc course, remember from tomorrow, you have to have an online teaching. I think all of us are struggling with online teaching, but there are lots of advantages on teaching a digital model. There are disadvantages. I will not talk about it. Advantages are anytime, anywhere, anyone, anything. Today, when you teach, somebody from California can join your teaching. You can teach anytime. We are not bound by 10 to 5 or 8 to 5, whatever. So I think there's a lot of opportunities, online teachings, to take it positively. Technology-enabled tools are going to come up. And I think education is going to make a major change after the COVID. Even when the COVID is passed away, many of these takeaways we are going to take. There are lots of computer-intensive tools which have come up in learning, computer-aided research, in data analysis, simulation. You can see computer in simulation of virus. So those are things which are going to integrate, and chemistry is going to bring them together, all the computer tools. In fact, I think Professor Balram talked about computational chemistry and biology, different length scale. I remember in the morning, it's very important to realize that the computational science is a great integrator of physics, chemistry, biology. In fact, I must say a very famous quotation by Quetelet in 1828, 200 years back, when he said the more progress physical sciences make, the more they tend to enter the domain of mathematics, which is a kind of center to which they all converge. We may even judge the degree of perfection to which a science has arrived by the facility with which it may be submitted to calculation. It's very important to realize that today we realize that how has it changed? Not just because I'm working in computation that I'm talking about it. I think everybody has understood, even the experimentalists. You can use theory, computers, fast algorithms to solve complex equations, predict structure and properties of molecules, predict reactions, dynamics of evolution, model materials, and drug design, biological activities. Artificial intelligence and machine learning have become very important tools today in data science. In fact, multi-scale simulation itself, where you use quantum mechanics for small size, then classical mechanics for a larger protein, then mesoscopic simulation for polymers, and eventually to engineering simulation. I had a slide again because I could not show the slide. But it's very important to realize, I think Professor Balram had already shown a similar slide where how different length scales can be connected. And I think that's going to become very important. So when you look at chemistry, we have to look at it in a very holistic manner. It's not the conventional chemistry. The reason I'm saying, because you are starting the MSc course, and this is where you can put a benchmark. It's very hard for old universities and IITs even to change radically, but you are starting your new course, put the syllabus in the right frame. My final message, which is the final slide, I'll just read it out. To all the students, chemistry is a central science. All of us know materials. Again, Professor Balram said in the morning, materials, biology, everywhere chemistry is there, materials are. However, chemistry is changing. So there is a changing phase of chemistry. I told you, from structure to function, molecules to systems. Previously, we were interested in molecules. Today, we have to look at a system. We have to look at a device. Retro thinking, which means you first look at what you want to do and then design your molecule, design your system. So that's the retro thinking. So essentially, that means structure to function driven chemistry. Mathematics and data science will become a very important tools. Remember, however, organic and maybe inorganic chemistry are very attractive. Both of them are very attractive science, but don't forget, physical chemistry is important. G.N. Lewis said, What is physical chemistry? Everything that is interesting. It's a very famous quotation of G.N. Lewis. So remember that while organic and inorganic chemistry will continue to be attractive, physical chemistry is very important. Do not neglect. Again, because you are starting the MSc course, I have seen what has happened in many universities, many places. So I just want to give this final messages. I'm very happy to hear a galaxy of speakers today, including many of my colleagues from ICERS, and one more is going to speak in Ganesh. A galaxy of speakers today, starting from Professor Balram, Professor Satyamurthy, I think Sandeep Verma, Mukesh, so many people. Pradeep, my friend Vijay Mohan, Pillai. I mean, it's amazing lineup that Pullarao had done. I think it's Pullarau's. I must say, hats off to Pullarao. It's not easy to get all of them, even online. I must say, it's not easy. Jain Murthy, yeah, he was in the car. So I'm very happy that Pullarao, that you have done a great job, and I wish best of luck. I could have been probably showing something more if I had the slides, but somehow it failed from my laptop. So I'm joining from a mobile. It's a great thing. Do research, learn, innovate. Study, research, and innovate. That should be your mantra as IIT Tirupati goes up. Take advantage of IIT Tirupati. Take advantage of IIT Tirupati, the IT system. And I think you have a great hope. I'm very happy that many new centers have come up. One of them, I told you, atomic molecular science, optical science, which they have already started. Uma is also there. I think he would be also interested. It's a great thing. And I believe post-COVID, you will have a great role to play in the science education. Thank you again. And I wish the program great success. And just like others, I say inaugurate the program. I'm very happy to inaugurate, give this talk. And I wish Pullarao and his entire team great success. Professor Satyanarayana for great visionary of getting it done. And you have Ganesh by your side. So I'm sure it will be a great institution, a great MSc program. Thank you very much.
Thank you, Professor Pal, for sharing your wisdom and showing us the future direction in chemistry, and also reminding us the importance of collaboration between different institutes and different disciplines. Thank you, Professor Pal. Thank you once again.
Welcome.
So we are at the last of our program. So our last speaker is Professor K.N. Ganesh. He is the present founder director of IIT Tirupati. In 2006, he became the founder director of IIT Pune, and where he has served for about a decade. And in 2017, he has become the founder director of IIT Tirupati. Professor Ganesh has received many distinguished awards, which include Science Academy Medal for Young Scientist by Indian National Science Academy, CSIR Bhatnagar Award, Silver Medal for Chemical Research Society of India, J.C. Bose Fellowship, Third World Academy of Science Award, Shastra C.N.R. Rao Award in Chemistry, H.K. Firodia Award in Chemical Science, National Research Award in Nanoscience and Nanotechnology by DST, and many others. He is a Fellow of Indian Academy of Science, Indian National Science Academy, and the World Academy of Sciences. He has been elected as the Secretary, Biomolecular Chemistry Subdivision of IUPAC. He has contributed significantly in the field of biomolecular chemistry and drug development. I request Professor Ganesh to share his experiences and also to culminate the today's discussion in his concluding remarks. Professor Ganesh.
Thank you very much. I hope I'll be able to share the screen. Is it coming up or?
Not yet.
Is the screen
not yet,
coming
sir.
up?
We can see, yeah, it is coming up.
It is.
Okay.
Yes, please go to slideshow. Yeah, that's perfect, sir.
Okay. I will go to the, First of all, let me thank and congratulate IIT Tirupati for this wonderful event of launching the MSc course in chemistry by bringing so many stalwarts in chemistry from the country. I think I already see that the number of participants are dwindling. They're all rushing for their lunch. So I need to be brief. But let me just start saying that I'm in the same position as Professor Satyamurthy in the morning. To speak after Saurabh Paul, again, it's not very easy. In fact, I was secretly hoping that his internet won't work. But anyway, it's a wonderful to hear Saurabh Paul, and also after so many people, I don't think I can say anything new which they have not covered. Let me start just talking about just chemistry. Now you see this picture, in the morning you saw a wonderful picture of viruses by Professor Balram. I just want to tell you that small, simple organic molecules, inorganic molecules can also be equally beautiful. By the way, for students, this is not coronavirus. This is the crystal structure of an inorganic complex. Let me go to the next slide. Now, some of these phrases have already come in. Chemistry is the central. Everybody said that, but I want to add two more words, useful and creative. This is the definition which was given by Ronald Breslow, who was the president of American Chemical Society. It is central because it is the basis of many of the scientific disciplines like biology, geology, material science, chemistry, the central pillar. It is useful because it provides many materials which are essential to everyday life and, bettering human, veterinary, plant care, better food, environment, everything. And one of the most important thing about chemistry is it is a creative science. It designs structures with new and unique properties. We know that there are chemicals which are naturally occurring, which are called as natural products, but many of the industrially useful, practically useful products have also been unnatural because chemists create that. In that sense, a chemist is almost like an artist. You create something which is not present and which will be very, very useful into science. I have just shown the insecticide pyrethrin, which has a very unusual cyclopropane structure, and also the first contraceptive pill, which is norlutein, which again has a very unusual structure of acetylene linked at a spiral, at the carbon atom. So chemists are very creative, they're very useful, and they're very central. Now, chemistry in everyday life, it has been talked about, but I'm just putting a very nice, simple picture, which was, how to introduce chemistry at the class 12 level from book of Professor Riana Rao. And as you see here, all the terminologies, what you see, they're all everyday, utility values. So chemistry encompasses almost all the things, in everyday life, right from, housing, health, textiles, food, agriculture. It has an enormous importance for our daily life. Now, it also helps us understand, asking very questions about the nature, like why leaves, they fall down, why battery generates electricity, why bodies use food to maintain life. So it's a wonderful science. Now, in just one slide, I want to give you about the achievements of chemistry. A lot of people said about the interdisciplinarity, etc. I just want to give you some practical examples for you to understand that we just take chemistry for granted, not giving as much of importance as we give for other areas. For example, right away as you are hearing or as you are seeing the slide, there are a lot of chemistry is happening in your eyes. The vision, there is a cis-trans chemistry happening. When you smell something, a lot of chemistry happens. The taste, sour, sweet, bitter, all of it comes because of chemicals and chemical interactions. The whole of food science is nothing but chemistry. I think some couple of examples was mentioned. And not only just in human world, even in the animal insects world, plant defense systems, they generate pheromones. In a small animal, insects, communication becomes very important. They use chemicals like pheromones, etc. So chemistry is very important for the physiological responses of humans, animals, plants, etc. Now, most of the chemicals, as I said, quite a few are natural products, etc. I will come down to that. But most of the useful chemicals, what we do in our daily life, it comes from coal, oil, and natural gas. A lot of paints, what we require, dyes, textile, polymers, for example, Teflon, nylon, polystyrene, PVC. If PVC had not been there, I don't know where would our communication, internet, communication, etc. would be there. You must have seen lots of PVC cables, thousands of kilometers being lined. That is a product of chemistry. Polystyrene, Teflon, nylon, and Velcro. Beautiful chemistry there. It's a Velcro, how we can create the same polymer composition having two different kinds of physical properties which just stick together. Detergent, soap. It is so important, particularly under the COVID thing, the hand hygiene depends upon the soap. In fact, I was trying to look into internet to get some idea about what is the soap consumption, how it has gone up in the last 4 to 5 months. It's amazing because all these detergents are made out of petrochemicals. And if you think how much any one of us consume, how much of soap we consume per year, probably it will run into kgs, and you multiply by the population of the world and the country, huge amount of soaps are required. That's all supplied by the chemists. Plastics, perfumes, I don't have to go into any of these things. Sports, chemistry has a wonderful influence on sports. And the moment I say chemistry in sports, most people think of performance enhancing drugs. Not so. The tennis racket, the swimming jacket made out of nano jackets, the football, athletics, the shoes, the tracks, everywhere chemistry has made a difference. And if the performance of players are increasing, it is also partly due to the kind of equipments that they use. And chemistry has played a very, very important role. When it comes to lifestyles, plenty of construction materials. And today, lots of construction materials which are, performance-based materials, plastics, etc., are used, which replaces many times the natural materials with better, being light and performance-oriented. The whole entertainment industry, the TV, the liquid crystal display that you all see, either on your watch or in your mobile, everything is nothing but products of chemistry. Communication, computer, PVC, I also mentioned about that. All of them are involved, making of materials which gives the desired properties. In fact, chemists are involved in synthesis, not synthesis of molecules, but synthesis of properties. We define what are the kind of properties we require and then tune your chemistry structure for that. When it comes to human health, that is where chemistry has played the most important thing. The life expectancy, in about 50, 60 years back, our life expectancy was only about 45 or 50. But today, even in India, it is reaching up to 80. And this life expectancy age has increased because of availability of several medicines, antibacterials, anti-cancer agent, antihypertensives. There are several natural products are involved, like Taxol, streptomycin, penicillin, cephalosporins. Many of them have been converted by chemists into more desirable molecules from the drug properties. Synthetics like aspirin, diazepam, ranitidine. In fact, tremendous amount of, in the health region, the chemistry has played a very, very important. It is in fact still a little bit unacknowledged, but when you talk about health, we talk about biology, which is very important to understand the origin of diseases, a molecular origin of diseases, but the therapeutics, the chemistry has played a very, very important role. When it comes to, for example, cancer, cisplatin, one of the wonderful drugs which is used, doxorubicin, HIV, in fact, about 15, 20 years back, HIV was such a dreaded disease, but understanding the viral life cycle, the biology, helped us create drugs like AZT, DDC, RT inhibitors, etc. To some extent that today, it is not such a dreaded disease at all. It's almost disappeared, the HIV disease. But to replace it, we have now corona. And again, I think it was talked about that. If you want to find, remdesivir, HCQ, many of the drugs, which are all, again, products of chemistry. Many of them are repurposed drugs. They were initially invented for something, but now we can also use it for that. Now, when you go to not only disease therapy, but disease diagnostics is very, very important. The earlier you can diagnose the disease, the better the chances of cure. And this is where spectroscopy, probes, fluorescence, electrochemical sensors, magnetic resonance techniques, X-ray, mass, Raman spectroscopy have played a fantastic, amazing role in developing of diagnostics. The sensitivity has increased, whether it is diagnosing an organism or the product of a metabolite which tells about the disease. There is an amazing, this thing has happened in the area of diagnostics. Chemistry plays. Not only human and plant health, but but the plant health also becomes very, very important. Agrochemicals, insecticides, pesticides, fertilizers, antifungals, so many of them are the products of chemistry. When you come to nano, most of the things what I have sort of said here, they're all mostly organic materials. But inorganic chemistry comes into fore when we talk about nanomaterials. Sensors, drug delivery, electronics, implants, diagnostics. The nanotechnology is having a huge impetus, huge influence on the production of new age products. So again, chemistry comes to the fore of that in the design, in the synthesis, in the manufacturing, etc. And Professor Saurabh Paul and others have already alluded to the role of theoretical computational chemistry. It's very, very important. Theoretical computational chemistry, understanding why molecules work, what are their energetics, thermodynamics, kinetics. It will all help us create products with better structures. You can work about that. And that is become an irreplaceable tool in all the areas almost. In fact, any of these areas, what I have said, you add the theoretical and computational knowledge, you can get better products, you can improve the existing products also. Then you're all engineering students. I mean, IIT is an engineering institutions. So chemistry has a very strong interface with engineering. Not only just a laboratory making thing, but scaling up, manufacturing, process chemistry, biochemical engineering for the antibiotics, etc. It becomes very, very important, where chemistry has a very strong, influence with the partnership with engineering. So they go together. So, and I did not talk about, I don't have time to cover everything, the biology. Already, I think people have alluded to the role of chemistry in biology. In fact, one of my favorite things to ask students is, what happens when chemistry stops in biology? When chemistry stops happening in the cell, we call it death. So chemistry defines, the boundary between the life and the death. And we know that the molecular structure controls its function and the structure and the properties. So in biology, the only difference in the chemistry, what we do in test tube, and the chemistry, what happens in biology, is that, in a test tube, you cannot do 2 or 3 reactions simultaneously. It is always intermixing. You can't have A plus B going to C and X plus Y going to Z. A will react with X, B will react with Y. It is difficult to do simultaneously 2 or 3 reactions in a test tube without any interference. But look at the cell. Thousands of chemical reactions happen within a cell without any cross interference. That is the beauty of it. That chemistry, we have to understand that. Not only they do not influence each other, but they regulate each other. The production of one chemical regulates, if it is not required, then another one. And if those regulations fail, we call that state as disease. So understanding that chemistry, it is supramolecular chemistry, self-assembling chemistry, and that is the future challenge. And to understand that, we need to get into physics and other dimensions, other sciences as well. Now, Professor Vijayamohan has already talked about that in a very, the future of, requires, for example, energy, solution to energy, environment, sustainability, understanding atmospheric science, chemistry, and also making smart materials, without recourse to that, they react to the environment, either to the light, to the temperature, or to the pH, etc. They can react. All of these things, chemistry has a great influence. Chemistry is central to that. But I would again like to repeat what others said, not alone in its isolation, but it has to interact with other disciplines. It is really interdisciplinary, the science, but it is central to that. Understanding molecules is most important because understanding molecules will help us understanding their properties, and that will help us how to tune the properties, etc. So this sort of slide would give you the whole, the canvas of chemistry, what all it can do. Chemistry is, the central science. Already it has shown it. The achievements of chemistry are, enormous. Now, this is just a slide on the coronavirus, and just to tell you that, chloroquine, hydroxychloroquine, lopinavir, darunavir, ribavirin, remdesivir, all these were drugs which were actually meant for different purposes. Now, when a new disease comes, now the chemists have tried to find out how to repurpose the drugs to a new thing. But again, design of drug all depends upon the molecular interactions. Whether small or big molecules, they have to interact, and understanding the chemistry. That interaction depends not only on the chemical properties, the structure, shape, but also on the forces of interaction. Once we understand that, then it will help us design new drugs. It's just to flash because of its contemporary relevance. Now, let me have another 2 or 3 slides before I finish. I think this was again alluded to by Professor Saurabh Paul. Now, we have all joined MSc Chemistry, and there are institutions like IISER, JNCSR, etc., and IISc, which offer integrated PhD programs. MS plus PhD. After BSc, you can go to get the integrated PhD program, or you can have this 2-year MSc. After that, you might go to PhD in chemistry, or you may get into teaching, etc. But what do you do after PhD? You have several choices. One is to go to the conventional research, get a PhD degree, and then get into teaching research in academic universities, in national laboratories, DAE, ISRO, etc. And you can get into the discovery research in industries. You can also join private universities. So plenty of chances are there on the research side with a PhD in chemistry. Or if you are more inclined to get into developmental chemistry, you can get into national laboratories, R&D institutions, try to find out new applications, etc. Industry. That is what you are. That is the research and is the development. And if an analytical mind, there are lots of analytical changes. In fact, the whole chemistry is nothing but analytical. Somehow the analytical chemistry means people think of only titrations, etc. But whatever we do, it is all finally analytical chemistry. It's very important in pharma, agro, health, environment, and instrumentation, etc. becomes very, very important. You can also get into law, IPR. You can take up another courses after the PhD, entrepreneurship, and get into very, very niche areas of caring. Finance, you can get into that. Or if you're interested in management, you can get into management, study a management in addition to this, PhD plus something. So only PhD plus something if you have a lot of jobs waiting for you. Management, you can get to become the directors of the institute, etc. Now, there are other kinds of areas which are developing where a PhD approach plus a chemistry background would be very, very helpful. For example, which we are going to start in, ISA is called as the regulatory science. Now, regulatory science, food science, forensic science, science journalism, they all become very, very important. Again, these are.
So, what do you advise in Japan?
I'm sorry, I'm getting some feedback. Somebody is talking with their phone. And then when you do all this thing at the end of the day, what happens? As a scientist, chemistry, it is also true for other areas. You get a very highly rewarding. What are the rewards? You can have publications. I think this is something which is true. All of us, many of us who spoke today, you can also actually saw Professor Satyamurthy mentioning his latest paper in molecular physics. You may publish 100 papers, 200, 300, but still your 351st paper is as exciting as your very first paper itself. That is something very inbuilt into our profession. Publications, you can take patents, you can do consultancy. And finally, a career in science, etc., will give you a great sense of achievement. But I must say that achievement and a satisfaction. But by nature, scientists, we should never be satisfied because satisfaction leads to a comfort zone and it is not good for reactivity. So we should always feel there is something inadequacy and try to reach, as Professor Rao says, the limitless ladder of excellence. We have to keep going, keep going. There is no end point at all. And that is the most beautiful thing of science and also research. In research, you realize that solving one problem leads to another problem. It is not a dead end. And the more you know, the more you don't know. You just realize that you do not know. And these are the important things about the science as well as in chemistry. So joining as a chemist, you have plenty of job opportunities. In fact, the chemistry, chemical and allied industries, they employ the largest number of people. People swayed away by the job opportunities in IT and other things, but chemical industry and allied industry, they employ the largest. Now, also I say allied industry, now it also comes into biotechnology, pharma, agriculture, everything involved. So ranging from analytical chemists to atmospheric, I will not go into the details. You will have an opportunity to get into job opportunities, plenty of that. So there is an intellectual challenge, there is an academic challenge, there is a societal thing, and of course, plenty of job opportunities exist by, with the chemistry. Now, I'll just take 2 slides, which, on topic which have not been mentioned by others. I'm sure all of you are going to take online classes. I hope I'm right, Professor Pullarao. You are not having them physically, you're going to teach them online.
True.
Now, yeah,
it's online.
Yeah, so I must tell students, it's a new experience for students and also for teachers to give online teaching. Now, this online course, Professor Saurabh mentioned that you can do it from anywhere, anytime, etc. But you want to succeed in online, participation. First of all, you must think that online course is like a real course. You must take it as seriously as that. Although you may not be seeing the teacher physically, except on the screen, Matthew. And also you must hold yourself accountable. One can give hundreds of reasons in online course, not effective, I did not understand, it is not good, etc. But you are also an equal partner, accountable. And for that, you must learn how to participate and get the best benefit of online courses. First thing is you must practice time management. You are taking this online course from home, and it is not very easy sitting at home. You have to isolate yourself. When you are taking a class, it should be like a physical class. Nobody should disturb you. You must create your own regular study space and stay organized. It is possible. And you must eliminate distractions, while taking the class. Don't do several other things, concentrate, and you figure out how you learn best. Different students have different methods of learning. You have to figure out what is the best way of learning. You want to take notes, or you just want to hear a recording of the thing. So you must talk to your faculty and find out. You actively participate in the learning process. And you must also, one of the good things is that this online thing will also permit for you to create your own network with other students. You can create discussion groups. Whatever you do not understand, you can talk to them. And please do interact in chat packs. Most of the online courses, there is a chat box available. One of the good things is that in a class, you may feel very shy to ask questions. You may always think that, oh, this question would be stupid, but in a chat box, you can always put it. So this is an advantage. And if the teacher has no time to answer, and your friend might answer that. This is an advantage that you can ask questions which you are shy normally to ask. And also, that kind of questions, when the teacher goes through, it gives him an instant feedback. Okay, by looking at the questions which you are asking, you can immediately, he has explained a point you did not understand, you can post a question. So at the end of the day, when the teacher looks at it, he will understand where he was clear, where he was not clear, etc. And of course, we know that in-person interactions, classroom is very important, both for students as well as for teachers. As somebody mentioned, the teacher is happy that he's not going to see the dozing students, sleeping students, etc. in the class. But online, we should, now that we do not have any other choice, we must see how best we can leverage this online interaction. But I must tell you that the faculty also must learn quite a lot. It is not easy to translate an in-person classroom into an online class. They have to accommodate themselves, they have to tune themselves, and every lecture, you must make sure that you just don't, leave with a PowerPoint thing, but you come on the screen for direct interactions, maybe 5 minutes, 10 minutes. Students should see you, in the open grid mode. You must make it a practice. And hope someday in the near future, I think we all revert back to our old times of having regular classroom. And, that is very important. And also, not just a class, it's actually stressful. I know last 3 hours we have been watching this Zoom. I'm sure all of us are tired. It's very, very important. It's very difficult actually to sort of glue onto the screen for a long time and hear. And it is not as effective as hearing somebody in person. It is there. But so you must also create your own space to have other interactions, online clubs. You must keep physically fit, etc. And it needs collaborative efforts from both students and faculty. In fact, I think I must mention this. Pularao is from IIT Bombay. We recently had a very nice lecture by Sahana Murthy from IIT Bombay, giving tips for the teachers, how to give online classes. I think both teachers and the students must know how to make it very effective. It's not very easy to translate. Use of technology is a must. One of the things which many people do not think, everybody at the policy making, they say you start the online class teaching. 25% of our students do not have access to laptop. They do not have access to internet connection. If both are there, their power goes away. It happened today itself, internet going off. So this is something which the government must address. We talk about smart cities, but if you do not have a good internet connection, how do you create a smart city? People will not be able to have access to information. And this is something at the highest level. How do you increase the bandwidth? How do you make it easily accessible, affordable? Internet is very, very important. So there is no other, you should not study through a mobile. You must buy a laptop. You must have a laptop and an internet connection. There is no escape from that. Not only technology, but also you must adopt yourself to the online teaching things. And the expectations and methodology may be different compared to the online in the classroom, but the outcomes are, very similar. So I would like to end by saying chemistry is our life, our future. Professor Mukesh, said that based on the International Year of Chemistry slogan. It is, there is no escape from that. It is our life. It is our future. Because as we said, all the future problems of energy, environment, pollution, sustainability, everything depends upon how we manage our chemicals. It's very, very important. So with a lot of other disciplines emanating from the chemistry concept, because this chemistry is central, but somehow it doesn't have the glamour. Suppose you say that you have joined chemistry, it is not looked upon with the same glamour as a high energy physics or some other data science and other kind of things. But so in this context, chemistry serves everything. It is like Cinderella without a fairy godmother. There's a lot of hard work for everything, but no one appreciates. And we should be proud of chemistry, because you can create so much to the society by a creative chemist. So I have shown chemistry is everywhere. And I must say that, the question which Professor Balram said in the beginning, that somebody was asked, can you name something which is not a chemical? I tried that for several sessions with high school students, etc. Nobody could come back. Till one day, one of the students asked me, is vacuum a chemical? I'm just putting it across. That was, I got stunned, I did not know how to answer that. Is vacuum a chemical? Because that see, it is a lack of something is, creates vacuum, but that's how the students are creative. So what I would like to say is that even if you don't like it, chemistry has a negative perception in the society. When people think of chemistry, they only think of explosions, pollution, gas cylinder, that factory thing, what happened in Vijayawada, etc. They're all negative perceptions, but I think we must build up a positive perception, right from making the N95 masks, to whatever is required. It all requires, chemistry knowledge. So even if you don't like it, you cannot avoid it. You better start liking it. And I hope, students would start liking it, and then you can make a wonderful career out of that. So I would like to thank you and wish you all the best. I hope when, the doors are open, we could get all the students, the MSc students someday to come and visit IIT Tirupati also. And I think we had a discussion in which, some of our faculty could give them the lectures. I hope it is still on. And similarly, we want IIT Tirupati. And as it was mentioned initially, we were born on the same day. We are almost like twins, IIT Tirupati and IIT Tirupati. And it so happens that myself and Professor Satyanarayana, we stay next to each other. And both our initials are KN, KN. So many people think that we are brothers also. There's nothing wrong, I mean, KN Satyanarayana and KN Ganesh, we stay together and we are in regular touch, and we would like to build a new model because Tirupati is the only city in which there is an IIT and IISER. The other city is Bhubaneswar, where there is a NICER and an IIT. So in these cities, we must build up a new model of interaction because we know, individually we cannot achieve it. We must complement each other. We should not duplicate facilities. So we have plenty of things we have been discussing with each other, and our campus are also very close to each other. From a practical point, we can do wonderful things. And I hope the students who have joined today and other chemistry students and the faculty will have good interaction between the two institutes. And with this thing, and you had a very good distilled information, I'm sure, I think it's all recorded, and I'm sure the institute will provide this recording. I hope you will also provide this recording link to us, because there are so many things which even experienced people like us can learn from our senior colleagues and friends. With these things, again, thank IIT Tirupati and wish students all the best. Thank you.
Thank you, Professor Ganesh, for showing us many fascinating aspects of chemistry and also the important tips for online teaching, both for students and teacher. I would also like to thank for your kind support throughout the year we are getting and in future as well. And yes, indeed, we are recording the whole session and it has been live broadcasted in YouTube. After the end of this session, we can surely send you the link. Thank you, sir. Now I request our HOD, Professor C.P. Rao. He wants to say a few words.
Yeah. Just I would like to say a couple of things. I do certainly realize.
Professor Ganesh, can you please stop sharing your screen, Professor Ganesh?
How do I do that? I'm looking for the
on
button.
top. On top, you will see stop sharing. Zoom window on top, red color.
Okay.
Yeah. Thank you. Thank you.
Yeah. So I just have one or two things, not too much. See, I do certainly realize that the time given to every speaker is very short. I know that. But I thought I would bring many of the people to the notice of these youngsters. That is only the main idea. Secondly, we have already planned a program which is called the Beyond Classroom. Of that, one of the component is Beyond Classroom connecting to great minds. So in that, in next 1 year, we will be covering a large number of eminent people in the country and probably even abroad we can start. And in the next 2 years, probably we'll be exhausting most of the connectivity. So please kindly bear with me for giving such a short period of 10 minutes to everyone. I do realize that it is a too short kind of thing, but we have methods by which we would like to learn a lot from our colleagues across the country and abroad in the time to come. And that is a plan of our master's, PhD, as well as for the entire chemistry community that we have at IIT Tirupati. And that will help not only chemistry department, even others in the institute at IIT Tirupati. And we would like to see these hopefully as a manual program rather than an online kind of thing as the time progresses, perhaps in the early next semester. So it was really, it's a little longish program, but I didn't want to cross the limit that was set by IIT Tirupati Senate, that we should not expose the students in any given day more than 3 hours or at most 4 hours of screen time. And I thought I would follow that, and more or less we are in that kind of a line. So that is the reason where I had to cut short the time given to individual. But thank you very much. And we have a formal vote of thanks by Dr. Gandeepan. Professor Satyanarayana, would you like to say something, Professor Satyanarayana?
Yeah, sorry, I had to step out for about 45 minutes for a review meeting, selection committee meeting that I had to attend. But I was there for most part. So thank you. I really want to thank everyone, all the senior chemistry colleagues from across the country for joining us. I think Professor Rao has achieved his objective of letting everyone know that that IIT Tirupati chemistry program is arrived, and it's got its master's program going on. And many of you have helped us earlier also in advising us, in selecting our faculty members and so on. I request your continued support in guiding us as we grow. Thank you very much.
So before we go for our formal vote of thanks, I noticed that Professor Mukesh has joined. So I request Professor Mukesh to share a few words to our students. Yeah, Professor Mukesh, please unmute your mic. Yeah.
Yeah, I hope you heard me. I'm sorry for the technical issues, and I shared my thought about working at beyond the boundaries. That I benefited, and many of my students feel that they are benefited, and we never stop learning, and we continue to learn, and as students, as faculty. And that is important because we don't learn everything at any given time. So we continue to learn, and the learning should never stop. And I wish the students all the best.
Thank you, Professor Mukesh.
Okay. So now I request my colleague, Dr. Gandeepan, to give the formal vote of thanks.
Yeah. Good afternoon, everyone. It has been a very energetic, engaging, and fascinating morning to all of us. Please bear me 2-3 minutes because it is my duty to thank each and everyone who are all supporting for this event. Let me begin with our honorable guests. We had really honorable chemists around in all over India. Professor B. Balram, N. Satyamurthy, Professor V. Chandrasekhar, Professor S. Umabadi, Professor J. N. Murthy, Professor Sandeep Verma, Professor T. Pradeep, Professor G.K. Lagri, Professor Vijay Moganan Pillai, Professor G. Mukesh, Professor Sauropal, Professor K. N. Ganesh. Respected professors, thank you very much. Thank you for joining us on this occasion. We are honored and we are blessed by your presence on this occasion of launching MSc Chemistry at IIT Tirupati.
Even you can decide your problems.
Thank you very much.
Sometimes that activity also I can how to design problem. So let's see. I just want to make this subject very interesting. Sometimes I do not really see.
Somewhere cross connectivity.
Okay. Yeah. Yeah, somewhere also someone talking.
Not one of our speakers.
Yeah. So yeah, we are fully charged and motivated to run on this long journey. Of course, we expecting the same support and your kind help for our future growth of our department as well as for our institute. Of course, yeah, that is the one thing we would like to request all of our eminent speakers and our guests. Next, I would like to convey my gratitude to our director, Professor K.N. Satyanarayana. Of course, he always show unconditional encouragement and support. And we are very fortunate having him an enthusiastic and very vibrant director to our institute. And so that we could progress very faster within this 3G IITs. Thank you very much, Professor K.N. Satyanarayana, Director, sir. Next, my heartfelt thanks goes to Professor C.P. Rao, HOD of our department. In fact, without his initiatives and his continuous effort, this great event would not be possible. And not only that, we are again fortunate having him and mentor for this very young chemistry department. In many ways, we are benefited as a faculty members and also to our new students and the existing students. Thank you, Professor C.P. Rao, sir. At the same time, I take this chance to thank our colleagues, Dr. Gauri Prasanna Roy, Dr. Arun Manna, Dr. Devashish Mandal, Dr. Rajiv Biswas. We are a very small family and work together to go along any works, whether it is conference or teaching or everything. So yeah, we are joint family. Thank you all for working on this event. Of course, our staff members also supporting for this event. Apart from our department, I extend my thanks to our administration department, academic section, and IT sections, who are all helping us to arranging this online event. Of course, I should not miss our students, the first batch of our MSc Chemistry, who are all deserve very big thanks for choosing us. And yeah, we are here to work for you. And not only our MSc students, we also thank our PhD students who choose our institute for their academic career. So we again welcome you all the students and thank you all for joining us. Before to end, I would like to thank all the participants from our institute, from other institutes who are all joining through the Zoom or watching us on YouTube Live. So for all of you, thank you very much and have a great day. Yeah, thank you all, sir.
Thank you all. Thank you all.
Thank you.
Thank you, sir. So we will take a leave. Yes.